In the vast expanse of the universe, there are mysteries so profound that they challenge everything we think we know about reality. Among these is a question that has haunted scientists for decades. Could there be stars that don't emit light, that exist in the shadows of the cosmos, yet wield unimaginable influence over the universe's structure? Welcome to the riddle of Axion stars, ethereal, invisible objects, theorized to be composed of a mysterious particle so elusive, it might hold the key to unlocking the deepest secrets of dark matter, gravity, and the very fabric of existence. These stars could be right in front of us, hiding in plain sight, yet they've managed to evade detection. But what if the stars we see in the night sky aren't the only ones that matter? What if the true nature of the cosmos lies in the invisible, the undetectable, the forgotten? As we embark on this cosmic journey, prepare to dive into a world where the boundaries of science, speculation, and the unknown converge, where Axion stars might just be waiting to reveal the most profound revelations the universe has to offer. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Axion stars are not stars in the traditional sense, not blazing balls of nuclear fusion, not white-hot spheres of plasma radiating light into the cold vacuum of space. They are, instead, quantum objects. Lumps of hypothetical particles known as axions, bound together not by the thermonuclear fire that powers suns, but by the quiet, steady pull of gravity and the strange rules of quantum physics. They are dark, invisible, nearly intangible, but potentially numerous, powerful, and cosmologically vital. Their existence could unravel the mysteries of dark matter, illuminate the quantum nature of spacetime, and explain why our universe behaves the way it does. To truly understand Axion stars, we must journey deep into the heart of particle physics, cosmology, and quantum field theory. We must peel back the layers of scientific understanding and trace the history of ideas, beginning with the problem they were born to solve, the strong CP problem in quantum chromodynamics. This problem, one of the great puzzles in theoretical physics, asks a seemingly simple question: why doesn't the strong nuclear force break charge parity symmetry, even though the equations say it should? The axion was invented to answer this question. First proposed in the late 1970s by Roberto Pecchi and Helen Quinn, and given its name by Frank Wilczek, the axion was meant to be a solution to a math problem. But in that solution lay the seeds of something far larger. Axions, if they exist, would be incredibly light, millions or billions of times lighter than electrons, and would interact very weakly with ordinary matter. In other words, they would be perfect candidates for dark matter, the unseen, undetectable mass that seems to make up about 85% of the matter in the universe. Unlike WIMPs, weakly interacting massive particles, another popular dark matter candidate, axions are ultralight bosons. And bosons, unlike fermions, do not obey the Pauli exclusion principle. This means they can occupy the same quantum state. When this happens on a large enough scale, something remarkable can occur: the formation of a Bose-Einstein condensate. Imagine trillions upon trillions of axions, cooled to near absolute zero, collapsing under the force of gravity. Instead of becoming a black hole, their quantum nature allows them to spread out into a diffuse, stable configuration. This is not a fusion-burning star. It does not shine. It is not even made of atoms. This is a macroscopic quantum object, a star made of axions, a gravitationally bound blob of coherent axion matter. It may span kilometers to hundreds of kilometers across. Its mass may vary from that of a small asteroid to that of an entire planet, or more. And it may have been floating undetected in the vast darkness of interstellar space for billions of years. But what do we know about their structure? Axion stars are governed not just by gravity but by the balance between gravity and quantum pressure. Their structure can be modeled using the Schrödinger-Poisson equations, which couple the gravitational potential to the wave function of the axion field. In the so-called dilute regime, the axions form a weakly bound state where gravity balances the quantum spreading. But in the dense regime, self-interactions between axions, arising from their nonlinear potential, become important. In this regime, axion stars may become unstable, leading to collapse, conversion of axions into photons, or the production of gravitational waves. The very existence of Axion stars has profound implications. If they are real, they may populate the dark matter halos of galaxies. They may collide with neutron stars, releasing bursts of radio waves detectable by our telescopes. They may orbit the centers of galaxies, influencing the motion of stars. They may even exist within our own galaxy, wandering invisibly between the stars. In some theories, collisions between Axion stars and other astrophysical objects could explain phenomena such as fast radio bursts, intense, millisecond-long blasts of radio waves whose origin is still unknown. Axion stars are not purely theoretical anymore. With the advent of high-precision astronomy, instruments like the Square Kilometre Array and the Very Large Array may detect their signatures. The Axions themselves might be discovered in laboratory experiments, such as ADMEX, Axion Dark Matter Experiment, MADMAX, or the Casper experiment, which aim to detect the tiny conversions of axions into photons in magnetic fields. If such a particle is detected, it would not only revolutionize particle physics, but also open a door into the cosmos unlike anything before. Let's step back for a moment and understand the quantum field that defines the axion. Axions are pseudo-Nambu-Goldstone bosons associated with a spontaneously broken global symmetry, the Pecky-Quinn symmetry. In the early universe, when the symmetry breaks, a field emerges, the Axion field, which takes on different values in different regions. As the universe cools, this field begins to oscillate. These oscillations store energy and behave like cold dark matter. But the field does not remain uniform. Tiny quantum fluctuations can grow under the influence of gravity, seeding the formation of compact objects. These are Axion mini-clusters, and in some scenarios, they evolve into Axion stars. The concept of Axion stars thus links the very small, the physics of fundamental particles, with the very large, the structure of the cosmos. It ties together quantum mechanics, gravity, cosmology, and astrophysics. It forces us to rethink what a star even is. No fusion, no light, no atoms. Just a massive, gravitationally bound quantum state. Their formation in the early universe is thought to begin with the fragmentation of the Axion field. As density perturbations grow, regions of overdensity form. These regions collapse under gravity, while the quantum pressure resists total collapse. Over time, they reach a stable configuration, a solitonic core, surrounded by a diffuse halo of Axion waves. These objects are sometimes called oscillatons or boson stars. They can have a rich internal structure, with nodes and interference patterns that arise from the wave nature of the field. Some models suggest that Axion stars may even act as seeds for supermassive black holes. In this view, dense Axion clumps could collapse into black holes in the early universe, explaining how such massive objects existed so soon after the Big Bang. Others propose that Axion stars might decay over time, converting axions into high-energy photons, neutrinos, or gravitational waves, offering new ways to probe the dark sector. Detecting Axion stars directly is incredibly difficult. They are cold, dark, and weakly interacting. But indirect detection may be possible. For instance, if an Axion star passes through a magnetic field, it could convert axions into photons. This is the principle behind many experimental searches. In astrophysics, a passing Axion star may cause lensing of background light or affect the timing of pulsars. In extreme cases, the gravitational collapse of an Axion star could produce gravitational waves, ripples in spacetime that we can detect with LIGO or future observatories like LISA. Theoretical models suggest a wide range of possible Axion star masses. In the dilute regime, they may weigh as little as 10 to the power of -12 solar masses. In the dense regime, they could reach 10 to the power of -5 to 10 to the power of -2 solar masses. Their radius is inversely proportional to their mass. The more massive they are, the more compact. Some models describe them as fuzzy dark matter cores, influencing galaxy rotation curves and helping to solve the cusp core problem in galactic halos. But the real mystery is this: are Axion stars common? If axions are the dominant component of dark matter, then there could be vast numbers of Axion stars drifting through space, undetected. Our solar system might already have encountered one. They may pass through planetary systems without a trace, or they may interact with neutron stars, leading to spectacular bursts of radiation. Some theories suggest that Axion stars may accumulate inside neutron stars, forming a central Axion core. If enough Axions accumulate, they may trigger a phase transition or collapse, potentially explaining some observed gamma-ray bursts. Others propose that Axion stars might generate periodic radio signals through coupling with magnetic fields, offering a new way to search for them. The implications stretch further still. If Axion stars exist, they could serve as natural laboratories for testing quantum gravity, general relativity, and the limits of quantum field theory. They could reveal the structure of the vacuum, the topology of spacetime, and the nature of symmetry breaking in the early universe. In string theory, axions arise naturally as moduli fields. Axion stars might then serve as probes into the hidden dimensions predicted by string theory. Their study is a frontier of science, blending cutting-edge theory, high-precision experiment, and cosmic observation. It requires collaboration between particle physicists, astronomers, cosmologists, and quantum theorists. It challenges our understanding of mass, light, energy, and the very fabric of existence. And so, the story of Axion stars continues, not as a footnote in theoretical physics, but as a potentially foundational element in the unseen machinery of the cosmos. To even begin grasping the magnitude of their possible influence, we must go deeper, into their theoretical predictions, the dynamics of their interactions, the exotic behaviors they may exhibit under extreme conditions, and how such behaviors might align with or diverge from the astrophysical anomalies we observe today. Let us start by examining the stability of Axion stars. Unlike conventional stars which are stabilized by thermal pressure resulting from nuclear fusion, Axion stars are stabilized by a delicate interplay of quantum pressure, gravitational attraction, and, in some scenarios, self-interactions between axions. In the dilute regime, the dominant balancing act is between gravity and the quantum uncertainty principle. Gravity tries to pull the axions inward, while their wave-like nature resists compression. This balance leads to long-lived, stable structures. However, when Axion stars reach higher densities, self-interactions, arising from the nonlinear nature of the Axion potential, begin to dominate. This introduces an instability, a tipping point where the star may either collapse into a black hole or explode in a cascade of radiation. This phenomenon is known as Bose-OVA, a kind of quantum detonation observed in laboratory Bose-Einstein condensates, and theoretically extended to astrophysical objects like Axion stars. If an Axion star absorbs more mass, either from ambient Axion fields or by accreting normal matter, it may cross the critical threshold and implode. During this implosion, axions are converted into photons, possibly gamma rays, or into other particles depending on the couplings permitted by the model. The result is a sudden and violent release of energy, similar in signature to certain unexplained astrophysical events like gamma-ray bursts, or even fast radio bursts, FRBs. FRBs are one of the most tantalizing mysteries in observational astronomy today. These are short, intense pulses of radio emission from distant galaxies that last mere milliseconds, yet carry more energy than the sun emits in days or even weeks. Several models have attempted to explain their origin, including magnet-ars, neutron-star collisions, or black hole mergers. But none of these models fully account for their characteristics, especially the repeating FRBs, which suggest a cyclical or non-terminal process. Axion stars colliding with neutron stars offer a novel explanation. When an Axion star enters the strong magnetic field of a neutron star, its particles can be rapidly converted into photons via the Primakov effect, essentially turning the neutron star into an amplifier for axion photon conversion. This mechanism could generate the precise radio frequencies and burst-like behaviors observed. Moreover, such collisions need not destroy either object. A glancing encounter could produce multiple bursts over time, explaining repeaters. The gravitational influence of the neutron star might even capture the Axion star into orbit, leading to periodic emission patterns. This hypothesis is currently under investigation, and while still speculative, It opens new doors for interdisciplinary studies linking high-energy astrophysics and quantum field theory. Another avenue of interest is gravitational lensing. Even though Axion stars do not emit light, they do bend spacetime through their mass. This means that if one were to pass between a distant star and Earth, it could lens the light of the background star, causing a temporary brightening. This microlensing effect has been used to search for MACHOs, massive compact halo objects, and could, in principle, detect Axion stars. However, since Axion stars can have a broad range of masses and sizes, and since they may not be compact in the same way as black holes or neutron stars, the lensing signal would differ. The shape, duration, and amplitude of the lensing curve could potentially reveal the unique signature of an Axion star, especially if combined with other detection methods. We must also consider the role of Axion stars in galaxy formation. In standard cold dark matter (CDM) cosmology, dark matter clumps hierarchically, forming small halos that merge into larger structures. However, this model faces challenges, especially at small scales. Observations show that dwarf galaxies often have cores with constant density, rather than the sharp cusps predicted by CDM. This is known as the core cusp problem. In the fuzzy dark matter model, where dark matter is made of ultralight axions, with masses around 10 to the power of -22 eV, quantum pressure smooths out the density profile, naturally producing cores rather than cusps. Axion stars could be the densest part of these fuzzy halos, acting as solitonic cores that stabilize the inner regions of galaxies. Their wave-like nature could also suppress small-scale structure formation, addressing the missing satellites problem, the observed lack of small galaxies compared to simulations. Now, consider the cosmological implications. If axions were produced through the misalignment mechanism, where the axion field begins displaced from the minimum of its potential in the early universe, then the resulting axion density depends on this initial displacement angle. Regions with larger displacements can produce denser axion clumps, which can evolve into axion stars. These stars could have formed as early as a few seconds after the Big Bang and may have survived to the present day. Their gravitational influence could affect the cosmic microwave background (CMB), large-scale structure formation, and even the reionization epoch. Axion stars could also interact with ordinary matter in subtle but detectable ways. For example, if one were to pass through the Earth, or more likely, through a detector placed in low Earth orbit, it could produce transient signals in highly sensitive instruments. This possibility has led to the proposal of new detection strategies using superconducting cavities, atomic interferometers, and precision magnetometers. Some concepts even involve launching specialized satellites designed to detect axion photon conversion in space, far from terrestrial noise. In more exotic scenarios, axion stars might interact with black holes in ways that reveal both their presence and the structure of spacetime itself. For instance, if an axion star falls into a rotating black hole, it could trigger a process known as superradiance. This occurs when bosonic fields extract rotational energy from the black hole, forming a boson cloud around it. These clouds can produce gravitational waves through their oscillations, leading to detectable signals for instruments like LIGO, Virgo, and the upcoming LISA observatory. The frequency of these waves depends on the axion mass, offering a way to probe axion physics through gravitational wave astronomy. Furthermore, the dynamics of these axion clouds can reveal violations of the Noether theorem, which states that black holes are fully described by mass, charge, and spin. The presence of a bosonic field like an axion introduces additional structure around the black hole that could be measured. In this way, axion stars and axion clouds may challenge our deepest assumptions about black hole simplicity and provide a window into quantum gravity. The connection to string theory cannot be overstated. Axions emerge naturally from compactifications of extra dimensions in string theory. Each compactified cycle in the extra dimensions can give rise to a different axion-like particle, ALP, leading to the so-called axiverse, a spectrum of axions with different masses and couplings. Some of these axions could be ultralight and act as dark matter. Others could be heavier and decay early in the universe. Axion stars composed of different axions could exhibit a range of behaviors and interactions, each with their own astrophysical signatures. In this view, the universe could be populated not by one kind of axion star, but by an entire best area of them, each tied to a different string-theoretic origin. It is also possible that axion stars contribute to the evolution of stars themselves. If axions exist and interact weakly with photons, they could be produced in stellar cores and escape, carrying away energy. This would alter the evolution of stars, especially white dwarfs and red giants. Observations of white dwarf cooling have already been used to constrain axion properties, but if axion stars exist nearby, their gravitational field could also affect stellar dynamics. Over time, axions could accumulate inside stars, leading to observable changes in luminosity, pulsation periods, or even triggering new forms of stellar instability. And what of the philosophical implications? If axion stars are real, they are invisible sentinels of the cosmos, undetectable by the naked eye, silent, cold, and vast. They challenge our anthropocentric understanding of what constitutes a star. They blur the line between matter and field, between classical and quantum, between the visible and the invisible. They force us to ask, how much of the universe is hidden in plain sight? How many objects pass through our sky every day without a trace? What secrets lie in the quiet void between the stars? In many ways, axion stars are the ultimate cosmic paradox. They are both wave and particle, both field and object, both old and new. They are born from the earliest moments of the universe, yet they may still be forming today. They are part of the invisible scaffolding of galaxies, yet they may hold the key to phenomena we have observed but never understood. To continue our exploration of axion stars, we must now consider how their properties manifest under extreme cosmic conditions, those beyond what ordinary stars or planets can endure. We delve deeper into the heart of their structure, the mathematics behind their existence, and how even the smallest variations in fundamental constants or field dynamics could birth vastly different outcomes in the evolution of such an object. The internal structure of an axion star is defined not by layers of plasma or nuclear fusion zones, as is typical in main-sequence stars, but by the solutions to the nonlinear Schrödinger-Poisson (SP) equations or, in relativistic regimes, the Einstein-Klein-Gordon (EKG) equations. These are mathematical formulations where gravity is balanced against the quantum behavior of a scalar field. The scalar field in this context is the axion field, which obeys the Klein-Gordon equation, a relativistic wave equation. The gravitational potential comes into play through the Einstein field equations of general relativity, creating a self-consistent system. Solving these equations numerically reveals two primary regimes, dilute and dense. In the dilute regime, the star is composed of low-density axion matter, weak self-interactions, and a large radius relative to its mass. This form is often referred to as a mini-cluster, or solitonic core, and could be several kilometers to hundreds of kilometers wide with masses ranging from lunar mass up to planetary or stellar mass. These stars are incredibly fragile, with their quantum pressure barely offsetting gravity. Their detection is challenging, but their interactions with magnetic fields, gravitational lensing effects, or potential FRB emission make them tantalizing targets for indirect observation. In the dense regime, however, the self-interactions of the axions become non-negligible. As the axion field approaches values near the peak of its periodic potential, often modeled as a cosine potential, nonlinear effects cause the field to become highly dynamic. The axion particles may start to interact more frequently and strongly, potentially leading to critical collapse. At this point, a Bose-Nova collapse can occur. The mass of the star reaches a critical threshold, the Chandrasekhar-like limit for axions, after which no further stable solutions exist. The object either disperses violently in a burst of radiation, collapses into a black hole, or settles into a metastable state temporarily until it meets its end. What is particularly fascinating is the role played by temperature. While axion stars are cold objects in the classical thermodynamic sense, having no internal fusion and not radiating significantly, the field configurations within them can exhibit temperature-like behavior when analyzed via effective field theory. Their coherence lengths, oscillation frequencies, and even thermal fluctuations, if any arise through interaction with ordinary matter or cosmic rays, could all influence their lifetime and decay modes. For instance, as the Axion star moves through the galactic environment, interactions with dark matter halos, molecular clouds, or stellar winds may slowly siphon or accrete material, bringing it ever closer to a critical phase transition. And then we must consider rotation. In real astrophysical systems, very few things are perfectly static. Angular momentum pervades everything, from spinning black holes to rotating galaxies. If Axion stars possess angular momentum, they are no longer spherically symmetric solutions to the EKG equations. Instead, they morph into toroidal or ellipsoidal configurations, leading to vortices and more complex behaviors. Rotating Axion stars may emit gravitational waves through quadrupole moments, or interact more dynamically with surrounding space. These rotating configurations, often referred to as vortons in related field theories, may have greater stability in some regimes and may behave more like dynamical solitons than stationary solutions. A rotating Axion star might also produce peculiar effects on surrounding plasma or magnetic fields. Due to the Axion's coupling to electromagnetism via the Chern-Simons term in the Lagrangian, Axions in strong magnetic environments can generate oscillating electric fields or induce changes in polarization. This leads to the tantalizing possibility of detecting Axion stars not through their gravity, but through the patterns they imprint upon light from background sources, distorting, polarizing, or even dimming it in unexpected ways. Moving from theory to technology, the next leap is in how we might detect Axion stars more directly. Most modern Axion searches, like the ADMEX experiment, are built to detect axions in the galactic halo using resonant cavities to catch axion to photon conversion under strong magnetic fields. However, Axion stars bring a new frontier. They may not only increase local axion density during passage near or through detectors but could produce transient electromagnetic signatures if their fields oscillate coherently enough. The idea of transient axion detection has led researchers to design time-domain axion detectors that rely on sudden shifts in cavity resonance, brief photon spikes, or anomalous thermal signals in otherwise isolated environments. Even gravitational wave detectors, such as LIGO and Virgo, might register the passage or interaction of large enough Axion stars, especially if they merge with neutron stars or black holes. Let us now explore the conceptual cosmological origins of Axion stars further. The early universe was an incredibly dynamic environment. In the first fractions of a second, quantum fields fluctuated wildly, and symmetry-breaking phase transitions led to the emergence of the standard model particles and potentially the Axion field. If the Pecci-Quinn symmetry was broken before inflation, the entire observable universe today would have the same Axion phase. But if it broke after inflation, the Axion field would exhibit spatial variations, leading to the formation of topological defects such as Axion strings and domain walls. These defects can decay, releasing copious amounts of axions. Through gravitational cooling and wave interference, these axions could condense into coherent clumps, the primordial seeds of Axion stars. Over billions of years, these seeds may have coalesced through gravity, forming larger bound objects. They might cluster in galactic halos, orbiting quietly and undetected. They may act as the gravitational glue for dwarf galaxies, or as disruptions in stellar streams. In fact, numerical simulations suggest that the mass function and spatial distribution of Axion stars may mirror or even outnumber that of traditional cold dark matter substructures. There's also the possibility of binary systems. Just as ordinary stars form binary pairs, so might Axion stars. A binary Axion star system would emit gravitational radiation as it orbits, and if the masses were large enough, these waves could be detected by space-based interferometers like LISA. Even better, if a binary system merged, the resulting collapse could emit both gravitational waves and electromagnetic radiation, a multi-messenger event of extraordinary uniqueness. One of the most curious ideas under development is the idea of Axion star catalysis. Imagine a scenario where an Axion star, through its gravitational field or coherent oscillations, triggers or enhances certain rare processes in ordinary matter. It could catalyze decays, flip nuclear spins, or even alter particle production thresholds. Though speculative, such processes might explain rare events observed in underground neutrino detectors or cosmic ray experiments. Let us now imagine what it might feel like to be near one of these objects. A spacecraft approaching an Axion star would detect no light, no heat, no magnetic field, but it would feel something, a strange shift in inertial guidance, an unexplained curvature in its path, a whisper of gravitational warping in the absence of visible mass. Instruments on board might register oscillating fields with no known source, or phase shifts in electromagnetic waves. A probe passing through the core of a dilute Axion star might experience minute changes in atomic clock precision. Quantum sensors might buzz softly with signals outside the standard model. The Axion field, oscillating at kilohertz or even gigahertz frequencies, would be like passing through a ghost, undetectable by most measures, but faintly real to those prepared to perceive it. This possibility has sparked discussions about launching specialized Axion detection satellites. These would use superconducting materials, squids, or atomic lattice clocks to detect even the most subtle interaction with the Axion field. Some even imagine coordinated constellations of satellites, spaced across thousands of kilometers, measuring minute changes in phase or polarization to triangulate Axion star passages. As we advance toward this technological frontier, the theoretical groundwork continues to evolve. Advances in lattice field theory, numerical relativity, and quantum gravity are slowly converging toward a fuller picture of how Axion stars might form, evolve, and die. Theories of modified gravity, extra dimensions, and quantum cosmology are being adapted to explore what role Axion stars play not just in this universe, but potentially across many. Indeed, if the multiverse hypothesis holds true, and each universe in the cosmic foam has different fundamental constants, then some may have axions that are far more or less massive, more interactive, or more stable. In these universes, Axion stars could be dominant actors, radiating energy, shaping galaxies, perhaps even forming the basis of exotic chemistry. In one universe, they may outnumber atoms. In another, they may serve as the only form of compact matter. But even here, in our known universe, the mystery remains tantalizing. Every time we look into the night sky and see a patch of darkness, we must now ask, is there something there? Is the darkness truly empty, or does it shimmer with the presence of an invisible giant, a ghostly Axion star, holding within it the quantum memory of the early universe? We are only just beginning to ask the right questions. The answers, as they come, will not only reveal new facets of the cosmos but will deepen our understanding of matter, energy, and the subtle dance that governs their interaction in the quiet, hidden realms of space. As we drift further into the cosmic enigma of Axion stars, it becomes increasingly apparent that these entities are not just isolated theoretical curiosities. Instead, they may serve as key pillars in our pursuit of understanding the deepest mysteries of the universe, from the true nature of dark matter to the architecture of spacetime itself. One particularly compelling aspect is how Axion stars interact with gravity on both classical and quantum levels. Gravity, the weakest of the fundamental forces, typically dominates at large scales. But Axion stars represent a strange reversal of this hierarchy. Gravity shapes them, binds them, but must constantly be in equilibrium with the quantum mechanics of the Axion field. This interplay blurs the lines between macroscopic and microscopic physics, suggesting that Axion stars are the clearest bridges we currently possess between general relativity and quantum field theory. For decades, scientists have sought a unification of these two pillars of modern physics. String theory, loop quantum gravity, and other attempts have proposed various mechanisms, yet none have yielded definitive, testable results. Axion stars, however, may offer a natural laboratory in the universe where this unification is not a distant theory, but a living, oscillating phenomenon. The concept of gravitational cooling is one of the mechanisms that help Axion stars form. As Axion particles gravitationally attract one another, they can fall into a bound state. The process is not simple collapse, it is moderated by the emission of scalar radiation, allowing the clump to lose energy without requiring interaction with other forms of matter. This cooling allows the Axion cloud to settle into a stable configuration. Over time, this can lead to the formation of dense cores and even binary Axion star systems. In some simulations, these clouds exhibit wave interference patterns, self-interacting like ripples in a pond, before achieving a stable configuration. Now, imagine these stable configurations moving through space. They're invisible to the eye, nearly undetectable to most instruments, yet they subtly influence their environment. In star clusters, they may shepherd stars into new orbits. In galactic halos, they may concentrate dark matter around them. They may pass silently through molecular clouds, disturb the fine balance of interstellar chemistry, or even induce structural changes in cryogenic systems on board passing spacecraft. But not all Axion stars remain in stasis. Some may undergo decay. The decay modes of Axion stars are governed largely by the interactions between axions themselves and their coupling to other particles like photons. One hypothesized decay pathway is through the axion-photon conversion, where oscillating axion fields in strong magnetic environments can generate bursts of photons, particularly in the radio and microwave ranges. These bursts may be transient and easily dismissed as noise unless we know precisely what to look for. In fact, a possible connection has been proposed between Axion stars and fast radio bursts, FRBs. FRBs are millisecond-scale radio pulses from deep space, often with no known progenitor. Some of them repeat, some do not. While many models exist, including magnet-Rs, neutron star collisions, and exotic plasma processes, Axion stars offer a tantalizing alternative. If an Axion star were to collide with a neutron star, or even just pass near it, the intense magnetic field of the neutron star could convert part of the Axion field into coherent radio waves. The result, a fast, bright burst from seemingly nowhere. What's more, if the Axion star survived the encounter, it could repeat the process, explaining the enigmatic repeating FRBs. Theoretical work has also explored whether Axion stars could seed structure formation in the early universe. In the standard model of cosmology, galaxies form around dark matter halos. If Axion stars formed early enough, shortly after recombination or even during radiation domination, they could act as seeds for baryonic matter to accumulate, forming stars, galaxies, and perhaps even black holes. This process, called Axion seeding, might resolve certain discrepancies in the small-scale structure problem, where cold dark matter simulations predict too many small galaxies compared to observations. Another tantalizing possibility is the role of Axion stars in the reionization epoch. After the cosmic dark ages ended, ultraviolet radiation from the first stars and galaxies reionized the hydrogen in the intergalactic medium. But the source of this radiation remains partially unexplained. Axion stars, if they decayed, interacted with magnetic fields, or catalyzed certain high-energy processes, might have contributed to this reionization. Their ubiquity, longevity, and quiet energy release could make them ideal hidden players in cosmic evolution. Now we turn to a more abstract, yet deeply fascinating, implication: the informational structure of Axion stars. If axions are fundamentally quantum fields, and if Axion stars represent coherent states of these fields, then they are not just physical objects, they are information processors. Much like Bose-Einstein condensates in laboratory systems exhibit emergent properties, Axion stars might encode complex information about the early universe, quantum fluctuations, or even entropy dissipation. Some theorists have proposed that Axion stars, especially in certain regimes, could act as natural quantum computers, solving problems in field dynamics, optimizing field configurations, or simulating the very spacetime they inhabit. Furthermore, their behavior might reflect certain principles of holography. According to the holographic principle, all information in a volume of space can be described by information on its boundary. If Axion stars contain dense field configurations, perhaps the information content of their interior can be fully described by their gravitational or electromagnetic signatures on the outside. This would be a profound demonstration of holography in nature, not in a black hole, but in a dark matter object. Let us now stretch our imagination even further. Suppose that Axion stars exist not just as coherent field clumps, but as nested structures. Could an Axion star exist within a black hole? Could Axion condensates surround neutron stars, altering their thermal evolution, magnetic field decay, or rotational inertia? Some models suggest that compact stars with Axion halos could explain certain anomalies in pulsar timing data, subtle, periodic variations in pulse arrival times caused by the gravitational and field interactions with Axion matter. And what about white dwarfs? These aging stars are known for their stability and long cooling times. If Axion fields permeate them or surround them in halo-like structures, their cooling rates might subtly differ. Observations of certain white dwarfs cooling faster than expected have already prompted studies into Axion emission as a cooling channel. Perhaps we've been seeing the fingerprints of Axion stars for decades, just not knowing where to look. Even Earth might not be immune to their influence. If a small Axion star passed through the solar system, it could induce shifts in planetary orbits, perturb satellite signals, or interfere with quantum sensors. While unlikely due to their presumed low number density, the possibility has driven interest in deploying Axion detection arrays in space, systems that could monitor large volumes of space for transient field fluctuations. In terms of energy, the Axion star is an incredible reservoir. Despite its ghostly presence, a typical Axion star might contain more rest energy than many human-made nuclear facilities. If humanity ever harnesses Axions, these stars could become the ultimate dark energy sources, compact, stable, and radiating only when provoked. However, the ethics and dangers of interacting with such exotic matter are profound. Would it be safe to extract energy from a coherent field? Could triggering one into collapse unleash uncontrollable forces? This question leads us toward another speculative branch, the use of Axion stars as interstellar communication beacons. Because Axion fields can modulate electromagnetic signals under specific conditions, it has been suggested that advanced civilizations could encode information into field configurations or Axion photon conversions, essentially using Axion stars as non-local quantum transmitters. These signals would be impervious to traditional noise and might remain undetected by civilizations not equipped to perceive axionic interactions. If this is true, it reframes the search for extraterrestrial intelligence, SETI. Instead of looking for radio waves or optical pulses, perhaps we should look for axionic modulations, frequency bands that do not conform to known physics, or light polarization anomalies near otherwise empty regions of space. Entire networks of communication could be humming quietly across the cosmos, using the very structure of dark matter as their medium. As we can now appreciate, the story of Axion stars is far richer than once imagined. From quantum oscillations to cosmological influences, from gravitational signatures to potential artificial manipulation, these objects stretch our understanding across almost every domain of physics. They are ghostly, silent, nearly invisible, and yet they might be everywhere. Their omnipresence, though hypothetical, opens the door to astonishing possibilities, not only about the nature of Axion stars themselves, but about the architecture of the cosmos at large. If Axion stars are common across galactic halos and filamentary structures, then the cosmic web we observe in large-scale structure surveys might be underpinned not merely by distributions of cold dark matter but by a lattice of coherent axionic objects. These structures could subtly influence galaxy formation, gravitational lensing, and even the CMB anisotropies. This idea brings forth the concept of a quantum backbone to the universe, an invisible, oscillating meshwork of Axion stars and fields that support the formation and evolution of luminous matter. Imagine the universe not as an empty void dotted with galaxies, but as a sea of interacting fields, vibrating across every scale, guiding the distribution of energy and matter. In such a framework, Axion stars are no longer fringe curiosities. They are fundamental to the cosmic scaffolding. The thermal history of the universe could also be significantly affected by the presence of Axion stars. Consider the era of matter-radiation equality, a pivotal epoch when the universe transitioned from being radiation-dominated to matter-dominated. If a substantial fraction of dark matter existed in the form of Axion stars at this time, then their gravitational and field dynamics might influence the growth of density perturbations and the subsequent formation of the first galaxies. Some simulations suggest that axionic clumps could enhance structure growth on intermediate scales, smoothing out certain anomalies in galaxy clustering data. Furthermore, we must examine the nonlinear regime of Axion star dynamics. Unlike classical particles that follow Newtonian trajectories, Axion stars are governed by the coupled Klein-Gordon and Einstein equations. Their field interactions are nonlinear, and under certain conditions, this can lead to phenomena such as soliton formation, gravitational collapse, or even spontaneous fragmentation. A large Axion clump might not remain coherent forever. It could bifurcate into smaller condensates, or collapse into black holes, or even explode in a burst of scalar radiation. This last possibility, Axion nova events, has become a topic of increasing interest. In these events, an overmassive Axion star becomes unstable and releases a significant portion of its energy in a rapid, bright outburst of scalar particles. Though hypothetical, such phenomena could explain certain unexplained energetic transients in the universe. They would be faint in visible light but strong in axion-like particle emission and perhaps gravitational waves, making them detectable only through specialized instruments. Speaking of gravitational waves, Axion stars offer another exciting frontier. While traditional sources of gravitational waves involve the inspiral and merger of massive compact objects, Axion stars may produce gravitational waves through entirely different mechanisms. Oscillating scalar fields in a dense Axion star can lead to quadrupole mass variations, especially in asymmetric configurations or during collisions. The resulting signals would lie in frequency bands distinct from those of black hole or neutron star mergers, potentially opening up a new spectrum of gravitational wave astronomy. The concept of Axion star collisions is itself a rich subject. In high-density regions like galactic centers or dark matter filaments, interactions between Axion stars could become more frequent. When two Axion stars merge, the resulting configuration depends on their relative phases, masses, and velocities. They might form a larger stable star, fragment into multiple smaller stars, or collapse into a black hole. Each of these outcomes would produce distinct observational signatures, ranging from scalar radiation pulses to gravitational wave chirps to exotic particle emissions. If Axion stars do collapse into black holes, it introduces another fascinating link to the black hole mass spectrum. There exists a gap in observed black hole masses, between the heaviest neutron stars and the lightest black holes, called the mass gap. Axion star collapse may be a pathway to forming black holes in this range, particularly in early cosmic epochs where baryonic processes were minimal. This could help explain the presence of primordial black holes without invoking new inflationary physics or exotic matter. And then there are hybrid stars, objects composed partly of traditional baryonic matter and partly of Axion condensates. These stars may arise when an Axion star is captured by a neutron star or when Axion matter accumulates within a collapsing gas cloud. The resulting object would exhibit hybrid properties, altered mass-radius relationships, anomalous cooling curves, and perhaps non-standard pulsation frequencies. Observing such objects would provide direct evidence of axionic field behavior under extreme conditions. The magnetic properties of Axion stars also merit close attention. Though axions themselves are electrically neutral, their coupling to photons means they can interact with magnetic fields. In dense environments, this coupling could induce magnetic instabilities, generate axionic current loops, or trigger coherent emission phenomena. There is even a theoretical framework for Axion magnetars, stars dominated by both strong magnetic fields and Axion condensates. Such stars might produce radiation spectra unlike anything we've seen, prompting some researchers to revisit odd or unexplained stellar spectra in archival data. Let's also revisit the Axion photon conversion mechanism, which lies at the heart of most detection strategies. When axions traverse a magnetic field, they can oscillate into photons, a process analogous to neutrino flavor oscillation. This conversion is highly sensitive to the strength of the magnetic field, the coherence length, and the energy of the axions. In astrophysical settings like magnetospheres, galaxy clusters, or even planetary magnetic fields, this process could yield observable X-ray, radio, or gamma-ray signals. In fact, several unexplained X-ray excesses in galaxy clusters have been proposed as Axion signatures. Now imagine a dense galaxy cluster filled with magnetic fields. As Axion stars pass through these regions, they might continuously convert a fraction of their mass into photons, creating a diffuse glow invisible to conventional surveys but detectable with tuned X-ray detectors. This diffuse light could represent one of the first indirect detections of Axion star populations, provided we can isolate it from background emissions. On Earth, laboratory experiments like ADMEX, MADMAX, CAST, and ALPS-2 are actively searching for Axion signals, mostly by generating strong magnetic fields and looking for photon conversion. However, these experiments are tuned to detect background Axion fields, not necessarily coherent objects like Axion stars. To detect Axion stars directly, we would need a paradigm shift in detector design, something capable of capturing transient field fluctuations, gravitational lensing from weak mass lenses, or even tiny timing anomalies in atomic clocks and quantum sensors. And yet, there may be a way to detect them indirectly through lunar occultation methods. If an Axion star were to pass behind the Moon, from our perspective, the gravitational lensing or slight field interaction could induce a tiny change in electromagnetic signal propagation. The idea is speculative, but the precision of modern space-based instruments like LISA or JWST might make such experiments feasible in the future. Theoretical physicists are also developing mathematical models to better understand Axion star stability, resonance frequencies, and decay modes. Using tools like the Schrödinger-Poisson equation or the Gross-Bataevsky formalism, they simulate the behavior of Axion fields under various initial conditions. These simulations often reveal surprises, sudden bifurcations, long-lived excited states, and even rogue wave analogues, sharp, transient spikes in field amplitude that resemble oceanic freak waves. One particularly curious result is the existence of oscillons, localized, long-lived field configurations that oscillate without dispersing. These may form spontaneously during Axion star interactions or during early universe phase transitions. Oscillons could serve as precursors to Axion stars or remnants thereof. They might even play a role in cosmic reheating, distributing energy and entropy across large volumes in a non-thermal manner. The broader implications for cosmology are staggering. If Axion stars, oscillons, and other scalar configurations were abundant in the early universe, then our models of nucleosynthesis, recombination, and even inflation may need revision. These objects could act as catalysts for matter-antimatter asymmetry, as reservoirs of early cosmic energy, or even as participants in cosmic inflation itself. There are even models where Axion fields drive inflation, the so-called natural inflation paradigm. In this framework, the inflaton field is a pseudo-Nambu-Goldstone boson, much like the Axion. If these two ideas are connected, then Axion stars might be the fossilized relics of the inflaton field, tiny pockets of the primordial scalar field frozen into coherence by the universe's expansion. Even more provocatively, some speculative theories propose that Axion stars could influence the fabric of time itself. In certain cosmological models, scalar fields interact not just with space and matter but with temporal gradients, slightly altering the local passage of time. If Axion stars have such effects, then perhaps they are not merely gravitational objects, but time-modulating ones. Imagine a spacecraft passing through an Axion field and experiencing a subtle change in clock rates, signal timing, or quantum phase coherence. These phenomena would be almost imperceptible, but not unmeasurable, especially with next-generation quantum technologies. In the coming decades, we may deploy space-based quantum interferometers, entangled particle detectors, or cryogenic atom arrays that could pick up the ghostly whispers of passing Axion stars. We are standing at the frontier of one of the most exciting and profound mysteries in modern physics. Axion stars are not just hypothetical particles glued together, they are bridges between theory and reality, between quantum fields and cosmic structure, between the visible and the invisible universe. They may ultimately represent an intersection point, where particle physics, cosmology, quantum field theory, astrophysics, and even information theory converge into a single, unified narrative of reality. The deeper we dig into the nature of Axion stars, the more we realize that they might be less about the particles themselves and more about the fundamental properties of existence: coherence, symmetry, information, and structure on cosmic scales. One of the most revolutionary ideas comes from the realm of holographic dualities. In some theories inspired by string theory, our universe may be a holographic projection of underlying information encoded on a lower dimensional boundary. If this is true, then Axion stars, particularly those with large field coherence and topological charge, could act like nodes or defects in that information fabric. They may represent concentrated packets of information that bridge the holographic interface, linking bulk spacetime geometry with quantum microstates on the boundary. This gives rise to an entirely new way of thinking. What if Axion stars are not merely gravitational condensates, but information processors? The phase coherence of the Axion field, its oscillations, its ability to superimpose and entangle across large distances, all of this points toward quantum information behavior. If Axion stars can interact not only gravitationally but also through quantum fields, then it might be possible they can exchange information, interfering or aligning in ways that affect other fields or particles. Such interactions might even be involved in regulating dark energy or vacuum fluctuations. Some theoretical frameworks, like the string axiverse, propose that our universe is filled with a wide spectrum of axion-like particles, each corresponding to different energy scales and dimensions. Axion stars in this picture could resonate with different vibrational modes of the vacuum itself. They might serve as nodes in a multidimensional standing wave of quantum reality, existing not in isolation but as harmonics in a cosmic symphony. Let's also revisit the idea of resonance. In nonlinear systems, resonance is a powerful concept. If Axion stars exist across a range of masses and field strengths, then under the right conditions, they could enter resonance with one another or with external fields, amplifying oscillations, transferring energy, or creating beat frequencies in scalar space. This could trigger chain reactions in Axion populations, akin to nuclear criticality. Such field detonations might be responsible for unexplained cosmic transients, or even large-scale structure features like cold spots in the CMB. Additionally, field resonance could allow Axion stars to form networks or filaments, coherent strings of scalar matter that oscillate in unison across interstellar distances. These Axion chords might behave like vibrational modes in string theory or as field conduits connecting galaxies. They could serve as invisible highways for dark matter, or as focal points for early galaxy formation. This brings us to another concept: scalar portals. In some models beyond the standard model, axions can act as portal fields, mediating interactions between visible matter and hidden sectors of the universe. If Axion stars can accumulate energy and then trigger scalar coupling events, they could momentarily open windows into other sectors, producing bursts of exotic particles, altering local field values, or even triggering vacuum transitions. While speculative, these ideas are being explored in cutting-edge theoretical physics and could explain certain anomalies in high-energy astrophysical observations. Moreover, there's growing interest in the role of Axion stars during cosmic reheating, the period just after inflation when the universe was repopulated with particles. Axion condensates formed during this time may have acted as field sinks or sources, redistributing energy in non-thermal ways and influencing baryogenesis, the matter-antimatter asymmetry, and the cosmic neutrino background. They might even explain why the universe appears to be slightly hotter in certain directions, a puzzle still unresolved. In terms of evolution, we must consider how Axion stars change over cosmic time. Unlike black holes or neutron stars, which are fairly stable unless perturbed, Axion stars are subject to internal field dynamics, external gravitational forces, and quantum tunneling effects. Over billions of years, a typical Axion star might oscillate, pulsate, absorb stray axions, lose energy through conversion, or even tunnel into a different vacuum state. These processes are incredibly subtle, but over cosmological timescales, they could lead to dramatic transformations. These long-term behaviors raise the possibility of Axion star life cycles, from nascent quantum clumps in the early universe to mature field structures today. Some might remain stable for billions of years, while others decay, collide, or evolve into different forms. Understanding these cycles is critical to mapping the landscape of dark matter and its role in cosmic history. Then there's the question of consciousness and information theory. While this lies well outside mainstream physics, it is worth mentioning that some speculative thinkers propose that coherent field objects, like Axion stars, might interact with the informational substrate of the universe. The high degree of phase alignment in Axion condensates resembles aspects of quantum entanglement and coherence thought to be relevant to theories of consciousness or integrated information. Though highly speculative, this idea proposes that Axion stars might act like cosmic neurons, storing, processing, or transmitting information across vast distances. Could it be that the universe is not merely physical but informational in nature, and that Axion stars are the firing nodes in this grand neural network? Again, this remains in the realm of philosophical speculation, but it underscores just how provocative and far-reaching the implications of Axion stars might be. Returning to the observable universe, Axion stars may also help explain certain long-standing anomalies in galactic dynamics. For instance, dwarf galaxies often exhibit flat rotation curves or unexpected density profiles that don't match predictions from cold dark matter simulations. A halo composed of Axion stars could produce smoother density distributions and less dynamical friction, aligning better with observational data. Moreover, their wave-like nature could suppress small-scale clumping, resolving the so-called missing satellites problem in cosmology. Wave interference between overlapping Axion stars could even lead to standing wave patterns in dark matter density, manifesting as shell-like structures or density ripples in galaxies. These would be invisible in traditional surveys but could influence the motion of stars, gas clouds, and even the lensing of background light. Some researchers have even suggested that the Milky Way might host one or more large Axion stars in its halo, possibly near the galactic center or along its dark matter filaments. If true, these objects could influence local gravitational potentials, alter stellar orbits, or produce subtle perturbations in the timing of pulsars. Monitoring millisecond pulsars with extreme precision could reveal timing anomalies consistent with Axion star interactions, making them a new kind of astrophysical probe. In terms of particle physics, discovering Axion stars would provide overwhelming support for the Pecky-Iquin theory and the existence of the QCD axion. This would solve the strong CP problem, validate new symmetries in the Standard Model, and open the door to an entire sector of scalar and pseudoscalar particles. It would also lend support to ideas like supersymmetry and string theory, which often predict axion-like particles in their low-energy limits. In fact, string theory predicts not just one axion, but potentially hundreds, each corresponding to a different compactified dimension or cycle in the extra-dimensional geometry. These axions could form stars, filaments, condensates, or even topological structures like cosmic strings or domain walls. The entire universe may be embedded in a vast axionic landscape, one that we are only beginning to glimpse. Axion stars, then, are not just another dark matter candidate. They are potentially the keystone to a whole new understanding of matter, gravity, and the universe itself. Whether through gravitational waves, quantum fields, cosmological evolution, or even philosophical speculation, these mysterious objects continue to stretch the boundaries of what we think is possible. And the journey doesn't end here. Each discovery brings new questions. Are there heavier analogues to Axion stars made of other particles? Could we one day manipulate or create Axion stars in the lab? Might civilizations in the far future use them as power sources, communication nodes, or even navigation markers in interstellar space? For now, we watch the skies, build our detectors, refine our models, and wait for the whisper of the stars that are not made of light. As our instruments become ever more sensitive, and as machine learning begins to play a greater role in data analysis, we may soon begin uncovering signals we previously dismissed as noise, subtle fluctuations in gravitational wave backgrounds, faint oscillatory patterns in stellar motion, minute deviations in photon polarization. Each of these could be a fingerprint left by an Axion star interacting with the cosmos. But these are not ordinary objects. They are profoundly different from anything we've encountered, because their essence lies not in mass, but in frequency, phase, and coherence. Their structure is not merely spatial, but temporal and field-based, shaped by the oscillation of scalar fields governed by ancient symmetries from the earliest moments after the Big Bang. Let's now consider a possibility that few would dare articulate openly in mainstream science, but one that lingers on the edge of theoretical consideration: the idea that Axion stars may be capable of interacting across cosmological distances not via particles or radiation, but through field synchronization. Just as quantum-entangled particles maintain correlations across vast distances, so too might regions of the universe with similar Axion field values resonate or couple, forming a kind of field telepathy. If so, then the universe is not only interconnected through gravity and electromagnetism but also through hidden scalar fields that may act as background carriers of cosmic information. This leads us into the speculative but thrilling realm of emergent spacetime. In some models of quantum gravity, space and time are not fundamental, but emergent properties that arise from entangled quantum information. Axion stars, as coherent field structures, may be more real, in some sense, than space-time itself. They may represent pre-geometric nodes from which local patches of reality condense. This reframes everything. Instead of seeing Axion stars as inhabitants of space, we begin to see space as an emergent illusion built from the collective behavior of such field configurations. And this brings us to a sobering realization: our entire picture of the universe may be a kind of cosmic projection. In this picture, Axion stars are like the deep nodes in the source code, the kernel threads, running on the universal operating system. Everything else, stars, galaxies, black holes, even time itself, may be higher-level constructs built on the dynamics of these field-theoretic substrates. Even within established physics, the very way Axion stars form may be unlike any other astrophysical process. In standard stellar evolution, matter collapses under gravity, heats up, fuses, and either stabilizes or explodes. But Axion stars form via coherence, not heat. They condense from field fluctuations that overlap in phase space. Imagine waves rolling through the quantum foam of the early universe. Some of them align just enough to create standing waves, which then attract more of themselves, amplifying into localized, self-sustaining field condensates. This is Axion star formation, and it is as much a quantum algorithm as a physical process. What's more, the scale-free nature of Axion stars means they can potentially form at multiple sizes. From subatomic clumps smaller than atoms to massive configurations as large as asteroids or even moons, their properties are governed more by field strength and boundary conditions than by ordinary matter laws. This fractal-like nature suggests that the universe could be filled with Axion stars across a wide spectrum, hidden not just in the vast voids of space, but potentially even near Earth, orbiting the Sun, or lodged deep within planetary cores. Indeed, some researchers have wondered whether unexplained geological or atmospheric phenomena on Earth might be due to tiny Axion star interactions. Could small, passing Axion stars occasionally tunnel through our planet, causing transient changes in electromagnetic field strength or gravitational potential? Could they influence seismic activity in subtle ways? These ideas remain highly speculative, but as detection methods improve, we may begin to correlate anomalies with precise sky positions and discover patterns invisible to us until now. On the technological frontier, if Axion stars can convert to photons under strong magnetic fields, as many models suggest, then artificial magnetic traps could one day allow us to study them in the lab. These Axion mirrors might reflect or absorb specific scalar field frequencies, allowing scientists to map their properties like a scalar field spectroscopy. Such devices could lead to new forms of communication that rely not on electromagnetic waves, but on coherent field pulses, scalar messaging across the vacuum, unaffected by electromagnetic interference or gravitational distortions. In the far future, if humanity survives long enough, we might learn to harvest Axion stars for energy. Their field dynamics could be tapped to extract coherent energy bursts, a form of scalar fusion. Because they don't rely on high temperatures like thermonuclear reactions, Axion-based energy might be safer, cleaner, and more stable. Moreover, as they are effectively invisible to ordinary matter unless actively converted, they represent a kind of cloaked power source, ideal for space-based civilizations that wish to remain undetectable. This brings us to an even bolder idea. What if advanced extraterrestrial civilizations have already discovered Axion stars and are using them? If so, then traditional SETI searches may be missing the signal entirely. Rather than broadcasting via radio waves or lasers, such civilizations might communicate by modulating Axion field oscillations, effectively whispering across the vacuum in a language of scalar harmonics. This would be entirely invisible to us, unless we began to look for it. Perhaps, then, the discovery of Axion stars will not only expand our physics, but also our place in the cosmic community. Perhaps they will teach us that the real channels of communication in the universe are not light or sound, but rhythm, phase, and coherence. Returning to the observational frontier, several experiments are now racing to detect the QCD Axion, or its broader Axion-like cousins. Projects like ADMEX, Axion Dark Matter Experiment, MADMAX, Magnetized Disk and Mirror Axion Experiment, and CASPER, Cosmic Axion Spin Precession Experiment, are using novel techniques to sense the ultra-weak interactions of axions with electromagnetic and nuclear fields. While none have detected definitive signals yet, the parameter space is vast, and many theorists are confident that it is only a matter of time. In parallel, gravitational wave observatories like LIGO, Virgo, and CAGRA are beginning to scan for unusual waveforms, ones that might arise from boson-star mergers, axion-star collapses, or scalar wave interference. These signals would differ from typical binary black hole or neutron star events, appearing more like diffuse, low-frequency oscillations or quasi-sinusoidal bursts, subtle, but distinctive. And then there's the global network of pulsar timing arrays, which may hold the key to detecting the gravitational influence of large Axion stars. These arrays use the hyper-precise signals from millisecond pulsars as natural atomic clocks. If an Axion star passes near Earth, or if a network of them warps the local gravitational field, these timing patterns would shift ever so slightly. Decoding these shifts could reveal a hidden map of dark structures moving silently through the cosmos. What's more, because Axion stars can also interact through photon coupling, radio telescopes like FAST and the Square Kilometer Array may eventually pick up transient electromagnetic signatures, brief flashes or spectral shifts that indicate axion photon conversion in magnetized regions. Coupled with gravitational and field-based detectors, this would represent a new era of multi-channel astronomy, what some are calling scalar astronomy. In the broader cosmic context, the study of Axion stars may even reshape our understanding of time. Scalar fields, unlike vector fields, evolve in complex, often cyclic ways. Some models suggest that regions of the universe dominated by axion-like condensates may experience time differently, slowing, accelerating, or oscillating in their own field-defined rhythms. This could lead to a new definition of cosmic time, one that is relative not just to gravity but to scalar field densities and coherence. In such a view, different regions of the universe may age at different rates, not due to relativistic time dilation, but due to scalar dynamics. This could resolve some of the paradoxes of early universe cosmology, where causally disconnected regions appear strangely uniform. If axion fields synchronize time across distances through coherent oscillation, then perhaps the early universe was never truly disconnected. Such revelations would not only transform physics but philosophy. They would call into question our notions of causality, simultaneity, and even determinism. If field coherence can synchronize regions of spacetime, then perhaps free will itself, long a thorny problem in physics and philosophy, may be redefined in terms of field dynamics, not particle interactions. Indeed, at the deepest levels, axion stars seem to invite us to rethink what it means to be real, to be connected, to exist. They are not simply hypothetical stars made of hypothetical particles. They are symbols of a new order of understanding, where matter, energy, time, and information converge into a seamless whole, structured not by atoms but by phase and field, by resonance and rhythm. As we continue this journey into the unknown, let us listen closely. For somewhere out there, among the stars we cannot see, the Axion stars are singing. Their song, however faint, reverberates through the fabric of the cosmos. It is not a sound in the traditional sense, not a vibration in air or even a ripple in space-time, but a modulation in field strength, a harmony of scalar waves resonating with the deep logic of the universe. If we learn to hear these harmonics, we may gain access to information not transmitted in light or matter, but embedded in phase relationships and temporal coherence. The pursuit of understanding Axion stars, then, becomes something more than astrophysics. It becomes an exercise in deciphering the background language of reality itself. To appreciate the magnitude of what Axion stars might represent, we must consider the nature of quantum fields. Every known particle corresponds to a quantum field that permeates all of space, and the particles themselves are simply localized excitations of these fields. In this sense, the universe is not made of particles, it is made of fields, and everything else arises from the structure, interference, and entanglement of these fields. Now, imagine a localized region of coherent field oscillation, an Axion star, not as an object floating in space, but as a self-stabilizing song in the quantum orchestra, where the Axion field is playing in perfect resonance with itself. This resonance is what grants Axion stars their unique stability. Unlike neutron stars or white dwarfs, which balance gravitational collapse with degeneracy pressure, Axion stars balance collapse with their own field pressure, specifically, the gradient and kinetic energy of the oscillating scalar field. As the Axion field concentrates and its amplitude grows, it becomes increasingly stiff, in a field-theoretic sense. The star's own internal oscillations provide the pressure to resist further collapse, creating a balance that is both delicate and enduring. But the balance can be broken. In certain scenarios, an Axion star can become unstable, either by accreting more field density from its surroundings, by interacting with another Axion star, or by entering a region of intense gravity. When this happens, it may undergo what is known as boson collapse, a violent implosion that can convert a large portion of the Axion field into relativistic particles or photons. In these moments, a silent and invisible object may suddenly burst into observable radiation, releasing a signature flare that briefly lights up the dark. Detecting such events would provide direct evidence of the existence of Axion stars and offer a new way to study scalar fields in the wild. However, the prospect of such detections depends heavily on our theoretical models. Many of these models are derived from analogies to Bose-Einstein condensates in condensed matter physics, where large numbers of bosons occupy the same quantum state. In a laboratory BC, the wave function of each particle becomes entangled with the others, leading to macroscopic quantum phenomena like superfluidity or quantum vortices. Similarly, in an Axion star, the scalar field behaves like a giant BC stretched across kilometers or even larger distances, oscillating in phase with itself, forming coherent structures on an astronomical scale. This analogy goes deeper still. In a BC, coherence and interference can produce solitonic structures, waves that propagate without spreading, maintaining their shape due to a balance between dispersion and nonlinearity. Axion stars, in many formulations, are exactly that, solitons in field space. They are the cosmic analogues of laboratory solitons, except instead of forming in cold atom clouds, they form in the scalar fields of the early universe, shaped by the symmetry-breaking processes of inflation and reheating. Understanding how such solitons arise from the quantum vacuum requires digging into the mechanics of spontaneous symmetry breaking. At high energies, the universe is thought to be governed by symmetric field configurations, states where forces and interactions are unified. As the universe cools, these symmetries break, like ice crystals forming in supercooled water. New particles emerge, fields split, and potentials reshape. The Axion field is believed to originate from just such a breaking, specifically, the Pecchi-Quinn symmetry, proposed to resolve the strong CP problem in quantum chromodynamics, QCD. When this symmetry breaks, it generates a field that can settle into different values in different parts of space. These values are like the initial phases in a giant oscillator, and where they vary smoothly, they can create standing wave patterns, regions of aligned oscillation that condense into Axion stars. In this picture, Axion stars are the fossilized echoes of a primordial field orchestra, still playing the same tune billions of years later. Such a model suggests that Axion stars are not rare, exotic anomalies but rather fundamental features of the cosmic landscape. Structures that may have been forming since the earliest epochs of the universe, evolving silently alongside galaxies and black holes, hiding in the intergalactic voids, whispering in scalar code. And if this is true, it raises a profound question: could Axion stars influence cosmic structure formation? Might they play a hidden role in shaping the scaffolding of the universe? We already know that dark matter is essential to galaxy formation. It provides the gravitational wells into which ordinary matter falls. If a significant fraction of dark matter is made up of axions, and if those axions clump into Axion stars, then these stars may act as the seeds around which galaxies and clusters assemble. This is not merely conjecture. Some simulations suggest that scalar field dark matter, also called fuzzy dark matter, can suppress small-scale structure, leading to smoother galactic cores and avoiding the cusp core problem observed in many dwarf galaxies. If Axion stars are the dense clumps of this scalar field, they could provide both the gravitational center and the smooth distribution needed to match observations. Moreover, these same simulations indicate that Axion stars may merge over time, forming larger and more complex structures. In doing so, they may emit gravitational waves, experience boson collapses, or trigger electromagnetic flares. The life cycle of an Axion star, then, could be as rich and varied as that of ordinary stars, except played out in the hidden language of fields and coherence. But how would we detect such a life cycle? That remains the great challenge. One possibility is through indirect observation. If an Axion star passes through a dense magnetic field, such as near a neutron star or within an active galactic nucleus, it could undergo axion-photon conversion, producing unusual radiation bursts. Alternatively, gravitational lensing studies might reveal invisible masses that don't match expected stellar populations, missing mass, events caused by the lensing of background light by compact, dark objects. In the future, missions like the James Webb Space Telescope and next-generation gravitational observatories like LISA, Laser Interferometer Space Antenna, may provide the precision needed to detect these subtle effects. Axion stars, while invisible in most bands, may cast shadows in spacetime itself, shadows we are only now learning to see. But detection is just the beginning. Understanding Axion stars may unlock new technologies. If we can learn to manipulate scalar fields, if we can build devices that interact with Axion fields as naturally as we do with electromagnetic fields, then we may gain access to entirely new forms of energy, communication, and propulsion. Scalar waves could transmit information without interference. Scalar field engines might harness coherence instead of combustion. Scalar computing systems could perform calculations not through silicon, but through the manipulation of phase and amplitude in a field matrix. All of this sounds like science fiction, but so did black holes a century ago, and quantum teleportation just decades ago. The study of Axion stars, by pushing us into the heart of field theory and coherence, may force us to rewrite not only our textbooks, but our future. And still, we return to the silence. Because that is the paradox of the Axion star. It is both present and hidden, massive and ephemeral, structured and soft. It challenges our senses, our instruments, and our intuitions. It demands not just observation, but reorientation. It asks us to think in waves, in coherence, in phase, not in particles and positions. As we continue to develop the theories, tools, and experiments needed to study these fascinating objects, we must remain open, not only to new data, but to new ways of seeing. For in the end, the Axion star is not just an object in space. It is a mirror to our understanding. It is a question written in the language of fields, waiting for us to learn how to read. As we peer deeper into the quantum nature of reality, the existence of Axion stars urges us to reevaluate our foundational assumptions, not only about what constitutes matter and energy, but about how the universe encodes and reveals information. In traditional models of astrophysics, phenomena are explained in terms of particles, forces, and interactions governed by classical or relativistic frameworks. But Axion stars operate at a crossroad, an arena where general relativity meets quantum field theory, where coherence replaces collision, and where waves of potential shape the observable universe without direct interaction. They are part of a new cosmological language, one that whispers rather than roars, curves instead of collides, and sustains reality through phase harmony. It becomes increasingly clear that if Axion stars truly populate the universe, then our current classification of stellar and substellar objects is woefully incomplete. Beyond the familiar categories of white dwarfs, neutron stars, black holes, and planets, there may be an entire taxonomy of scalar-based structures yet to be uncovered. These would not necessarily conform to the laws we associate with baryonic matter, nor would they emit radiation in ways our instruments are currently designed to detect. And therein lies the great puzzle. How many cosmic phenomena are we misinterpreting or simply missing altogether because we are looking for the wrong kinds of signals? Take, for example, fast radio bursts, FRBs. These incredibly brief and intense bursts of radio waves originate from extragalactic sources and have largely defied explanation. Could some of them be caused by Axion stars undergoing Bose-nova collapses or interacting with strong magnetic fields near neutron stars, leading to sudden axion-photon conversion? Some researchers have speculated exactly this. The nonlinear dynamics of axion field collapse, particularly under the influence of gravitational compression, can result in rapid energy release, possibly in electromagnetic form. If that energy finds a magnetic medium through which to couple into the photon field, a transient yet powerful signal could result. Further, there is the mysterious observation of anomalous cooling in white dwarfs. Some stars seem to be losing heat faster than standard models predict. One hypothesis is that axions, produced in the dense stellar interiors, are carrying away energy invisibly, acting as an additional cooling channel. If true, and if axion stars are aggregations of such axions in coherent form, then they may act not only as dark matter repositories but also as thermoregulators in galactic evolution. These subtler astrophysical effects may ultimately serve as indirect signatures of axion star influence on the visible cosmos. Now consider gravitational lensing. When a massive object passes in front of a distant star or galaxy, it bends the light from that background source, producing magnification, distortion, or even multiple images. Microlensing surveys have been used extensively to hunt for machos, massive astrophysical compact halo objects, as dark matter candidates. If axion stars exist in abundance, they might produce lensing effects similar to those of black holes or rogue planets, but without accompanying emissions. We might already be seeing their fingerprints in microlensing anomalies, blips and curves in light curves that don't match known profiles, but have been discarded as noise or unexplained artifacts. Some future observatories, like the Vera C. Rubin Observatory, formerly LSSD, are expected to produce immense time-domain datasets that track changes in the brightness of billions of stars. In these datasets, fleeting but telltale signs of axion stars might finally emerge, if we know how to look. But deciphering them will require new computational tools, tuned not for classical events but for the subtle imprints of scalar coherence on the night sky. Yet even more tantalizing is the role axion stars could play in the early universe. After the Big Bang, the universe underwent a series of symmetry-breaking transitions, cooling from a hot, undifferentiated plasma into the structured hierarchy of particles and fields we know today. During one such phase, the Pecchiaquin symmetry breaking, axions are believed to have been produced. These axions, if abundant and cold, would have formed a bath of ultralight particles permeating all of space. In this primordial broth, small fluctuations in density could lead to coherent condensation, resulting in the first axion stars. In this view, axion stars are not the remnants of galactic processes but rather the seeds, structures that predate galaxies themselves, gravitationally guiding the condensation of baryonic matter into stars and planets. If true, this suggests that the formation of visible structures in the universe may have been deeply intertwined with the invisible dance of axion coherence. Moreover, the coherence of the Axion field itself might play a stabilizing role in the evolution of large-scale structure. Some models suggest that coherent scalar fields can act as a kind of quantum pressure, preventing the overclumping of dark matter and smoothing out the violent fragmentation that arises in cold dark matter simulations. This could explain why observed galaxy distributions often appear more uniform than standard models predict. In this sense, Axion stars might act as regulators of cosmic harmony, tuning the tempo of structure formation, dampening turbulence, and preserving the elegant fractal distribution of matter we observe in the cosmic web. Their very presence, though invisible, would serve as a counterpoint to entropy, a quantum metronome ticking softly beneath the roar of spacetime. But the implications go further still. Some theories of inflation, the brief period of exponential expansion in the early universe, predict that scalar fields like the inflaton or axion could leave lasting imprints on the cosmic microwave background. These imprints might include non-Gaussian fluctuations, polarization anomalies, or even preferred directions. Axion stars, as coherent condensates of these early fields, may encode these primordial imprints in their structure, providing a fossil record of the inflationary epoch. In other words, by studying Axion stars, we may be probing not only the nature of dark matter or exotic physics, but the conditions of the universe in its very first moments. Axion stars might serve as time capsules of cosmogenesis, frozen relics of the field dynamics that birthed everything we see. Equally fascinating is the possibility of coupling between Axion fields and other exotic fields, such as those predicted by string theory or other beyond standard model frameworks. In string theory, for example, extra dimensions can give rise to numerous scalar fields, often called moduli or dilatons, that interact in complex ways. If axions are but one manifestation of a broader scalar sector, then Axion stars might be the simplest members of a larger family of field condensates. Some string-inspired models even suggest the existence of axiverse scenarios, universes filled with a spectrum of ultralight axion-like particles, each with different masses and interaction strengths. In such a scenario, multiple types of Axion stars might coexist, each corresponding to a different resonance frequency of the universal field. These could form a veritable menagerie of invisible structures, layered, nested, or entangled across scales we can barely imagine. The implications of such a universe are staggering. Not only would it redefine our understanding of cosmic structure, but it might also offer new paths for technological innovation. If we can detect and manipulate Axion fields, we could potentially create artificial Axion condensates in laboratory settings, scalar analogs of laser beams or quantum crystals. Such condensates might serve as the basis for new computing systems, energy storage methods, or even gravitational shielding technologies. Imagine a future where we use controlled Axion field gradients to warp spacetime, achieving propulsion without reaction mass. Or where communication is achieved through phase-modulated scalar pulses that pass unhindered through matter. Or where artificial coherence is used to slow down decoherence in quantum computing systems, extending coherence times indefinitely. These may sound like dreams, but they are dreams grounded in the fabric of the universe itself. For axions are not speculation, they are a prediction, born of the effort to reconcile theory with observation. Their existence would resolve deep puzzles in quantum chromodynamics, account for dark matter, and offer testable predictions across particle physics, astrophysics, and cosmology. And Axion stars? They are simply the logical consequence of Axion field dynamics under gravity, a structure that, given the right conditions, must emerge. So we are left with a choice: to consider the possibility, to build the detectors, to run the simulations, to develop the theories that will bring these silent titans into view. For in doing so, we do not merely solve a puzzle, we expand the boundaries of what we believe the universe can be. The Axion star is not just a thing in space. It is an idea, a possibility, that invites us to dream, to explore, to question. It challenges our senses, our assumptions, and our imaginations. And perhaps, in the end, that is its greatest power. As we continue our journey through the mysterious and mind-bending concept of Axion stars, let us turn now to an even deeper layer of understanding, one that bridges the observable universe and the intricate realm of quantum behavior. What sets Axion stars apart from traditional astrophysical objects is not merely their invisibility or exotic origin, but their uniquely quantum character. Unlike stars composed of atomic nuclei and electron clouds, Axion stars are governed by wave functions, not particle tracks, by interference, not collisions, by coherence, not chaos. To understand them is to abandon much of our classical intuition and instead embrace a reality sculpted by wave mechanics on a cosmic scale. In this new framework, gravity is no longer the sole architect of celestial objects. Instead, we find that the Axion field, the very field responsible for the existence of Axion particles, can shape its own structures through self-interaction and coherence. This means that Axion stars form not only because of gravitational pull but also because of the quantum pressure and collective behavior of the scalar field. This is entirely different from the way ordinary stars form from clouds of gas and dust compressing under gravity until nuclear fusion ignites. Axion stars need no fusion. They are not lit from within. They are harmonized into being. But what exactly does this harmony mean in physical terms? In quantum field theory, a coherent field is one in which all the particles are described by a single wave function that evolves in time. This wave function doesn't simply dictate where the axions are likely to be, it defines the axions themselves. In Axion stars, the Axion field is in a macroscopic quantum state, where the collective behavior of possibly trillions of particles results in a single, unified oscillation. You can think of it like a cosmic scale metronome, ticking, pulsing, waving through space-time. This coherence is what gives Axion stars their unusual stability. Whereas most aggregations of particles tend to collapse or scatter due to internal interactions, Axion stars are sustained by this coherent state. The self-interaction of the Axion field creates an effective potential that resists collapse, even when gravitational forces increase. This effect is akin to quantum degeneracy pressure in white dwarfs or neutron stars, but it emerges from field dynamics rather than particle exclusion. Now, if you were to map the density profile of an Axion star, you wouldn't find a hard edge or a solid surface. Instead, you'd see a smooth distribution that tapers off gradually, the density decreasing exponentially with radius. The central core is the densest and most coherent, but even the outer regions maintain phase alignment with the core. This wave-like structure results in interesting interference patterns when Axion stars interact with each other or with other gravitational bodies, and it could potentially lead to distinctive signatures in gravitational wave observatories if the events involve sufficient mass. Speaking of interactions, what happens when two Axion stars pass near each other? Unlike traditional stars, they don't necessarily collide and merge in a traditional sense. Their fields can overlap and interfere, leading to transient structures, wave packets that flicker into existence for mere seconds or minutes before dissipating. This kind of event would be undetectable in visible light or conventional telescopes. But it might leave behind a whisper in gravitational waves, or a brief disruption in background radiation patterns. There is also the tantalizing possibility of gravitational binding between Axion stars and black holes. A small Axion star orbiting a black hole might act as a field reservoir, gradually leaking its coherence into the black hole's ergosphere. This could catalyze exotic particle conversions or even amplify axion-photon coupling through frame dragging and spin alignment. Some theorists have even proposed that Axion stars could cloak black holes in a scalar field halo, an invisible shroud that modifies the way space-time curves around the event horizon. These ideas are not just theoretical play. Several active research efforts are focused on simulating Axion star interactions with known objects using high-performance computing and nonlinear field equations. These simulations often employ the Gross-Pitaevsky equation, a type of nonlinear Schrödinger equation used in quantum systems. This equation captures the self-interaction of the Axion field and allows researchers to model how the field behaves under compression, rotation, or external gravitational influence. And then there's the idea of rotation. Can Axion stars spin? The answer appears to be yes, but not in the classical sense. When a traditional star spins, its angular momentum is carried by the movement of its constituent particles. In Axion stars, angular momentum is carried by the phase of the field itself, giving rise to what are known as vortices. These vortices are similar to those seen in superfluid helium or Bose-Einstein condensates, where the wave function winds around a central axis, producing quantized rotational states. Such vortex-bearing Axion stars might possess internal structure far more complex than previously imagined, a lattice of field loops, each maintaining its own quantum number, locked in a cosmic ballet. Now consider the possibility of external stimulation. If axions are weakly coupled to photons, a premise central to many detection strategies, then electromagnetic fields can influence the axion field, and vice versa. In strong magnetic fields, such as those near neutron stars or magnetars, the axion field could be stirred, possibly inducing coherent conversion into photons. This process could result in sudden bursts of radio waves or X-rays, depending on the axion mass and local conditions. This has led to a growing belief that some poorly understood astrophysical phenomena, like anomalous radio pulses, unexplained gamma-ray emissions, or even periodic dimming in certain star systems, might be due to axion star-related effects. As we expand our observational capacity, instruments like the Square Kilometre Array, SKA, the Extremely Large Telescope, ELT, and even future missions like the Laser Interferometer Space Antenna, LISA, may be key to uncovering these subtle signals. These instruments will have the sensitivity required to detect the faint gravitational tremors or electromagnetic echoes that might accompany axion star behavior. But technology alone won't suffice. We need new algorithms, built not for traditional object detection, but for time domain analysis, signal reconstruction, and nonlinear pattern recognition. Machine learning, particularly deep learning, may prove instrumental here. By training neural networks on simulations of axion star behavior, we can teach our systems to recognize the subtle, non-Gaussian footprints that axion stars leave in data. Moreover, we must remain open to the idea that axion stars might manifest not just in the sky but even in our own labs. While the mass of QCD axions makes their lab creation impractical, ultralight axion-like particles, possibly emerging from string theory's axiverse, could, in principle, be simulated in condensed matter systems. Researchers have already developed analog systems that mimic scalar field behavior using trapped atoms, optical lattices, or superconducting circuits. These tabletop universes allow us to watch axion-like field dynamics in real time, explore collapse thresholds, and test interaction scenarios. If these analog systems reveal consistent behaviors, we will be one step closer to understanding how axion stars might behave in the wild. And this, in turn, can refine our astrophysical models, enhancing our ability to reverse engineer cosmic data and identify the invisible players behind the stage. The full recognition of axion stars in physics would be more than just a discovery. It would be a paradigm shift, a reevaluation of what constitutes structure in the universe. No longer would we think of stars as being exclusively made of burning hydrogen or degenerate matter. We would instead embrace a new category: stars made of fields, stars that do not shine but vibrate, stars that are silent yet fundamental. And this would force us to ask, how many other field-based objects are out there? If axion stars exist, why not stars made of other scalars? Why not composite field structures? Hybrid stars composed of multiple fields entangled together? Why not field domains that intersect with our spacetime only at certain frequencies or moments, existing in a form that defies classical dimensionality? These questions may sound metaphysical, but they are grounded in the mathematics of modern theoretical physics. We already know that vacuum states in quantum field theory can host topological defects, domain walls, monopoles, and cosmic strings. Could axion stars be just one form among many, an introduction to a much vaster menagerie of field-borne phenomena? And if so, what implications does this have for our understanding of the origin and fate of the universe? As we continue exploring the enigmatic nature of axion stars, it's clear that their potential to reshape our understanding of the universe goes far beyond their quantum mechanics. These stars do not simply reside in the distant reaches of space, waiting to be discovered. They could hold the keys to some of the most fundamental questions in cosmology, particle physics, and the very nature of reality itself. Their study pushes the boundaries of what we know about the universe's composition, structure, and the forces that govern it. However, to truly understand their significance, we need to probe deeper into the realms of quantum mechanics, dark matter, and the role of axions in the cosmic puzzle. Axions, at the core of these stars, are hypothetical particles that have fascinated physicists for decades. Proposed in the late 1970s as a solution to the strong CP problem, the issue of why strong nuclear interactions do not break charge parity symmetry, axions were initially introduced as a byproduct of quantum chromodynamics, QCD. In essence, axions were designed to explain a mystery that had eluded physicists for some time. Why is the strong nuclear force, one of the four fundamental forces of nature, so symmetric with respect to charge and parity? The axion was proposed as a very light, very weakly interacting particle that could, through its existence, account for this symmetry. But while axions were originally conceived to solve a problem in the world of particle physics, their implications extend far beyond that narrow scope. In fact, the discovery of axions could help unlock a number of mysteries, ranging from dark matter to the nature of gravity itself. This is because, in addition to their role in particle physics, axions are theorized to play a critical role in the composition of dark matter, the mysterious substance that makes up approximately 85% of the mass of the universe, yet cannot be directly detected by current means. Dark matter, which remains largely invisible to us, interacts only through gravity and weak forces, making it notoriously difficult to study. One of the most compelling theories regarding dark matter involves axions as a key component. In the early universe, axions could have been produced in vast quantities, contributing to the formation of dark matter. As such, the study of axion stars is not merely a pursuit of curiosity, it is a direct investigation into one of the most significant unsolved problems in astrophysics: the true nature of dark matter. Axion stars, if they exist, would be one of the first observable manifestations of axion dark matter. These stars could provide us with a direct probe into the properties of dark matter, revealing its structure, distribution, and potential interactions with ordinary matter. Their study could help us understand not only the properties of axions but also the broader properties of dark matter itself. Are axions responsible for all of dark matter, or do they only contribute a portion? What role do they play in the formation of galaxies, clusters, and the large-scale structure of the universe? These are the types of questions that could be answered by observing axion stars and studying their interactions with other cosmic phenomena. In addition to dark matter, axion stars also present a fascinating avenue for exploring the very fabric of space-time. As we delve deeper into the nature of these stars, we must consider how their quantum mechanical properties could influence the curvature of space-time itself. Axion stars, much like other compact objects in the universe, exert gravitational forces on their surroundings. But unlike traditional stars, the nature of this gravitational influence could be markedly different due to the underlying quantum field that governs the axion particles. It's possible that the unique gravitational signatures of axion stars could be detectable in future gravitational wave observatories, such as LISA, Laser Interferometer Space Antenna, or even more advanced detectors. By studying the distortions in spacetime caused by axion star mergers or interactions with other astrophysical objects, scientists could gain insights into both the quantum nature of axions and the broader behavior of gravity at the most fundamental level. These kinds of observations could provide a window into a new regime of physics, one where quantum mechanics and general relativity intersect in novel and unexpected ways. Furthermore, axion stars could have implications for our understanding of the formation and evolution of the universe itself. The presence of axion dark matter in the early universe would have had a profound impact on the way cosmic structures developed. As the universe cooled and matter began to clump together under the influence of gravity, axion particles could have contributed to the formation of dark matter halos around galaxies, providing a crucial scaffolding for the development of large-scale structures. By studying axion stars, we can gain insights into the conditions of the early universe, shedding light on how dark matter has shaped the evolution of galaxies and the cosmic web. One of the most intriguing aspects of axion stars is their potential to help us understand the nature of quantum gravity. Quantum gravity is the hypothetical theory that would unify general relativity, which describes the force of gravity on large scales, with quantum mechanics, which governs the behavior of subatomic particles. Currently, these two pillars of physics are incompatible, and no theory exists that can describe both simultaneously. The existence of Axion stars could serve as a bridge between these two domains, providing a way to probe the quantum nature of gravity in a regime where both effects are significant. This could open up entirely new avenues of research into quantum gravity, leading to a deeper understanding of how space-time itself behaves at the most fundamental level. As we continue to uncover the mysteries of Axion stars, we also confront the challenge of how to detect them. Since Axion stars are made of axions, which are extremely weakly interacting particles, they do not emit light in the same way that ordinary stars do. They are effectively invisible to traditional electromagnetic telescopes. This presents a significant challenge for astronomers, as they are accustomed to detecting celestial objects based on their light emissions. However, as we've seen with other dark matter candidates, indirect detection methods may hold the key to finding Axion stars. One promising approach is the search for gravitational waves. As mentioned earlier, the unique properties of Axion stars could produce subtle distortions in spacetime that might be detectable by advanced gravitational wave detectors. Mergers of Axion stars, or interactions between Axion stars and other objects such as black holes or neutron stars, could generate gravitational waves with distinctive signatures. By analyzing these waves, scientists could infer the properties of Axion stars and confirm their existence. Another possible detection method involves the interaction of axions with electromagnetic fields. As mentioned previously, axions are theorized to couple weakly with photons, especially in the presence of strong magnetic fields. This interaction could lead to the production of detectable photon signals under certain conditions. Experiments such as the Axion Dark Matter Experiment, ADMEX, are already attempting to detect axion photon conversion in laboratory settings, and similar methods could be applied to observe the electromagnetic signatures of Axion stars. Despite the challenges, the potential rewards of detecting Axion stars are immense. The discovery of Axion stars would be a groundbreaking achievement in astrophysics, offering profound insights into the nature of dark matter, gravity, and the early universe. It would also pave the way for future research into other exotic phenomena, such as primordial black holes, strange matter, and even the possibility of other types of quantum field objects in the universe. Axion stars represent a fascinating frontier in our understanding of the cosmos. These objects, composed of hypothetical axion particles, challenge our conventional ideas about the nature of stars and the structure of the universe. They offer a potential link between particle physics, cosmology, and quantum gravity, with the power to transform our understanding of dark matter, gravity, and the fundamental forces of nature. As we continue to search for these elusive objects, the questions they raise about the very fabric of reality are sure to push the limits of human knowledge, opening up new realms of discovery and adventure in the universe. The existence of Axion stars would mark a new chapter in the story of our universe, a story that is still unfolding, and whose ending is yet to be written. The search for Axion stars could also provide an essential tool for refining our understanding of astrophysical phenomena that we currently observe in the universe. Axion stars, as exotic as they might be, are not isolated anomalies. They would be part of the larger cosmic framework, and their discovery could drastically alter how we interpret other astronomical observations. By examining Axion stars, we may be able to reconcile certain phenomena that remain difficult to explain with existing models of the universe, potentially bridging gaps between theoretical models and observational evidence. One of the most exciting possibilities that the discovery of Axion stars would offer is a more refined picture of how dark matter interacts with regular matter. While dark matter itself is invisible, its presence is inferred through its gravitational effects on galaxies, galaxy clusters, and other large structures in the universe. The idea that axions could constitute dark matter suggests that their interactions with ordinary matter, though weak, may still leave subtle clues that can be observed. As such, the study of Axion stars could open up new avenues for detecting and understanding dark matter. This is particularly significant in light of the current efforts in both theoretical and experimental physics to detect dark matter directly. Experiments such as those looking for weakly interacting massive particles, WIMPs, or axion-like particles, ALPs, are ongoing, but the elusive nature of dark matter means that detecting it directly has proven incredibly difficult. Axion stars could serve as indirect detectors of dark matter. By understanding how axions interact gravitationally or electromagnetically with other objects, we may be able to gain a more direct probe into the properties of dark matter itself. Furthermore, the potential observation of axion stars might help clarify the role of axions in the larger structure of the universe. Currently, one of the key questions in cosmology is how galaxies and larger cosmic structures formed in the early universe. Dark matter plays a crucial role in this process, and understanding its properties is vital to understanding the formation of galaxies, stars, and planets. If axion stars exist, they could provide insights into the early universe's evolution, offering a snapshot of how dark matter contributed to the formation of the cosmic structures we observe today. They may even offer a window into the very first moments after the Big Bang, when the universe was still in its infancy, and the seeds of galaxies and stars were being sown. The study of axion stars is also significant in its implications for the future of space exploration. As our technology improves and we develop more sensitive instruments for observing the cosmos, it's possible that we will be able to directly detect axion stars or their influence on surrounding space. Gravitational wave detectors, radio telescopes, and optical instruments may all play a role in this search. The prospect of such discoveries could not only increase our understanding of the universe but also inspire new missions and technologies aimed at exploring the universe's most mysterious and elusive phenomena. One potential avenue for detecting axion stars in the future involves space-based telescopes. These observatories, free from the distortions of Earth's atmosphere, could provide more detailed and accurate measurements of cosmic objects. Space telescopes like the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope could potentially detect the faint signals produced by axion stars, offering new perspectives on their structure, behavior, and distribution in the cosmos. As new space observatories are launched, the prospects for discovering axion stars and studying their effects on the surrounding universe become more and more promising. Another aspect of the axion star phenomenon that deserves attention is the potential for these objects to influence the behavior of other exotic objects in space, such as black holes and neutron stars. These extreme objects, with their intense gravitational fields, could be ideal environments for axion stars to interact with other forms of matter and energy. The interactions between axion stars and these more massive objects might provide us with a unique opportunity to study extreme astrophysical conditions and gain insight into the fundamental forces of nature. In particular, understanding how axion stars influence the formation and behavior of black holes could offer critical clues about the nature of gravity and spacetime itself. Axion stars might also present an opportunity to study the so-called cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The CMB is an invaluable tool for cosmologists, as it provides a snapshot of the early universe, giving us a glimpse into the conditions that existed just after the Big Bang. If axion stars are indeed made up of dark matter, they could contribute to the CMB in subtle ways that we have yet to fully comprehend. By studying the potential interactions between axion stars and the CMB, we could gain more detailed information about the universe's early history and the formation of cosmic structures. Another fascinating implication of axion stars is the potential role they may play in the evolution of the universe's fundamental forces. The interaction of axions with gravitational forces, electromagnetic fields, and other types of matter could provide key insights into how the universe's fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are related. The search for a unified theory of everything, one that connects these forces into a single framework, has been a long-standing goal of physicists. The study of axion stars, and their potential to connect quantum mechanics with gravity, may offer a breakthrough in understanding how these forces interact at the most fundamental level. As scientists continue to refine their theories and models regarding axion stars, they will likely face new challenges. Theoretical work will need to account for the wide range of possible axion properties, including their mass, charge, and interactions with other particles. New experiments will need to be designed to probe deeper into the nature of these particles, pushing the limits of current technologies. And as more data is collected, researchers will need to develop novel ways to interpret and analyze this information in light of new discoveries. In addition to theoretical and experimental challenges, the search for axion stars will also require collaboration across a variety of scientific disciplines. Astrophysicists, particle physicists, cosmologists, and engineers will need to work together to design the next generation of instruments capable of detecting axion stars and their interactions with other cosmic objects. This interdisciplinary collaboration will not only advance our understanding of axion stars but also strengthen the broader scientific community's ability to tackle the most difficult and profound questions about the universe. The potential discovery of axion stars would be one of the most exciting breakthroughs in modern science, offering answers to some of the most profound mysteries in physics and cosmology. From dark matter to quantum gravity, the implications of these exotic objects would reverberate across numerous fields of study. While the road to discovering axion stars is still long, the possibility of such a discovery fuels our imagination and deepens our desire to explore the universe's deepest secrets. The search for axion stars is not just about finding a new type of celestial object. It is about uncovering the fundamental truths that underlie the universe itself. These stars could help us answer questions that have eluded humanity for centuries, from the nature of dark matter to the true nature of gravity. As we push forward into this new frontier, we stand on the edge of a new era in science, one that promises to change our understanding of the cosmos and our place within it forever. The pursuit of understanding axion stars will likely be one of the defining scientific endeavors of the 21st century. As we stand on the brink of this exciting frontier, we must also acknowledge the complexity of the work ahead. The discovery of axion stars would represent a leap in our understanding of not just dark matter, but the very fabric of space and time. This exploration could reshape our entire worldview, challenging established theories and offering new frameworks through which to view the cosmos. One of the key challenges in studying axion stars lies in their detection. Unlike traditional stars, which emit vast amounts of electromagnetic radiation, axion stars are not expected to shine in any conventional sense. Their very existence hinges on the subtle interactions of axions, particles that are incredibly weakly interacting with the rest of the universe. The fact that they might be undetectable by traditional means only adds to their mystery, making the search for axion stars a daunting and intricate task. The search for them is not merely about finding a new class of objects, but requires rethinking the ways in which we detect and measure celestial phenomena. This challenge also makes it all the more rewarding to even consider the possibility that axion stars could be observed in the near future. If they exist, they could hold the key to understanding the elusive nature of dark matter, one of the most significant puzzles in modern physics. Axions, as potential dark matter candidates, offer a more comprehensive explanation for the missing mass observed in galaxies and galaxy clusters. The revelation of axion stars would likely provide concrete evidence that dark matter is not just a theoretical construct but an essential component of the universe's structure. As researchers push the boundaries of astrophysical and quantum physics, the development of more sophisticated observational technologies will play a critical role. Innovations in particle detection, gravitational wave astronomy, and radio observations may enable scientists to capture faint signals from axion stars. These signals might come in the form of gravitational waves, which could be detected through instruments like LIGO or Virgo, or they could be electromagnetic signals detected by next-generation radio telescopes. With each new generation of technology, the likelihood of discovering these enigmatic objects increases. Moreover, as we continue to refine our understanding of axion physics, we may find ourselves unraveling the complexities of how axions could form stellar objects in the first place. Unlike ordinary matter, which primarily interacts via electromagnetic forces, axions interact through the weak nuclear force. This unique property could profoundly influence the formation and dynamics of axion stars. Their density, structure, and stability would depend not just on the properties of axions themselves but also on their interactions with the environment around them. This understanding could lead to new insights into the evolution of the universe, particularly in the context of the formation of cosmic structures like galaxies, stars, and planets. The role of Axion stars in galactic evolution is another intriguing aspect of their potential discovery. If Axion stars exist, they could offer important clues about the formation of galaxies and other large-scale structures. The interaction between Axion stars and the interstellar medium, the gas and dust that populate galaxies, could influence the way that galaxies evolve over time. If axions play a significant role in the formation of galaxies, this could change our entire understanding of how galaxies come together and grow. The mere existence of Axion stars could provide a missing piece in the puzzle of galactic formation, helping to explain how galaxies have evolved from the early universe to the present day. As we contemplate these possibilities, it's important to keep in mind that Axion stars could also be a significant source of gravitational waves. Gravitational waves, which were first detected by the LIGO Observatory in 2015, offer a new way to observe the universe. These ripples in spacetime, produced by the acceleration of massive objects, have provided researchers with valuable insights into black holes, neutron stars, and other exotic objects. If Axion stars are capable of producing gravitational waves, they could offer a new window into the workings of dark matter and provide critical tests for the theories surrounding these enigmatic particles. The detection of gravitational waves from Axion stars would mark a pivotal moment in our understanding of both axions and the broader fabric of spacetime. The connection between Axion stars and gravitational waves also opens up intriguing possibilities for future observations. If these waves can be detected, they could provide a wealth of information about the structure, density, and behavior of Axion stars. By studying the waves they produce, scientists could gain insights into the fundamental properties of axions, including their mass, spin, and interactions with other particles. These observations would not only help confirm the existence of Axion stars but also deepen our understanding of dark matter as a whole. In addition to their potential role in the production of gravitational waves, Axion stars could also provide clues about the nature of black holes. These two types of objects, while fundamentally different, share some similarities in their extreme properties. Both Axion stars and black holes are thought to interact with the fabric of spacetime in unusual ways. The study of Axion stars, in conjunction with black hole research, could offer new insights into the nature of gravity and spacetime. Understanding the behavior of Axion stars near black holes could lead to new discoveries about the nature of singularities, event horizons, and the extreme conditions that exist at the heart of these objects. The search for Axion stars is also an exciting example of how fundamental physics, cosmology, and astronomy are coming together. As scientists continue to probe the mysteries of the universe, it is clear that many of the most profound questions lie at the intersection of these disciplines. The study of Axion stars could provide a bridge between particle physics and astrophysics, offering new insights into the relationship between matter, energy, and the structure of the universe. It could also lead to new breakthroughs in our understanding of the fundamental forces that govern the universe, from gravity to electromagnetism to the weak and strong nuclear forces. The discovery of Axion stars would represent a monumental achievement in the field of astrophysics. It would not only provide a concrete answer to one of the most pressing questions in modern physics, the nature of dark matter, but also open up a host of new avenues for exploration and discovery. The study of Axion stars could offer profound insights into the formation of cosmic structures, the nature of gravity, and the evolution of the universe itself. As we continue to develop new observational techniques and refine our theoretical models, the search for Axion stars will remain one of the most exciting and promising frontiers in modern science. The journey into the mystery of Axion stars takes us deeper into the interplay between fundamental physics and cosmology. What makes this topic so uniquely captivating is the fact that it touches nearly every major unsolved problem in modern astrophysics. From the true nature of dark matter to the origin of structure in the universe, Axion stars sit at a crossroads of questions that have puzzled scientists for decades. And as more theoretical and experimental work unfolds, it becomes increasingly evident that these elusive objects may not just be peripheral oddities. They may be central actors in the cosmic drama. A key element in understanding Axion stars is how they relate to the concept of boson stars. Boson stars are hypothetical compact objects composed of bosonic particles, unlike conventional stars made up of fermions like electrons, protons, and neutrons. Axions, being bosons, are capable of occupying the same quantum state, thanks to Bose-Einstein statistics, which allows them to collapse into highly dense, coherent quantum configurations. This quantum coherence is not just a theoretical curiosity. It gives Axion stars their distinct structure and behavior. Unlike neutron stars, which are held together by neutron degeneracy pressure, or white dwarfs, which are stabilized by electron degeneracy pressure, Axion stars are bound by a delicate balance between quantum pressure and gravitational attraction. The wave function of axions extends across the star, and its self-interaction and gravity interact in a deeply non-classical way. The result is a celestial object that behaves less like a ball of gas and more like a giant quantum particle. In fact, some researchers describe Axion stars as macroscopic quantum objects, blurring the line between particle physics and general relativity. To understand how Axion stars might form, we need to explore the early universe. After the Big Bang, as the universe expanded and cooled, different fields began to take shape. The Axion field, if it existed, would have formed shortly after the QCD, quantum chromodynamics, phase transition. If this field were misaligned from its lowest energy configuration, it would start to oscillate as the universe cooled. These oscillations would produce axions. Over time, the axions produced from these misalignments could clump together under their mutual gravitational attraction, possibly forming bound structures, axion mini-clusters, or even full-fledged axion stars. This formation scenario also raises questions about the distribution and abundance of axion stars. If they formed early in cosmic history, they might now populate the halos of galaxies, moving silently and invisibly through space. Some estimates suggest that if axions are the dominant form of dark matter, there could be billions of axion stars in our own galaxy alone. They might even occasionally interact with ordinary stars or black holes, producing detectable signatures. One promising method for detecting axion stars is through their gravitational lensing effects. Like all objects with mass, axion stars bend the spacetime around them. If an axion star passes between us and a distant light source, such as a star or a quasar, it could briefly magnify that light in a characteristic way. These microlensing events could be picked up by dedicated surveys such as OGLE or MACHO, although distinguishing axion stars from other compact objects remains a challenge. But gravitational lensing isn't the only potential signature. Axion stars might also produce faint electromagnetic emissions under specific conditions. If an axion star were to pass through a strong magnetic field, such as the one surrounding a neutron star, it could produce photons through axion-photon conversion. This process, known as the Primakov effect, allows axions to transform into photons in the presence of a magnetic field. In theory, this could lead to brief radio flashes or other electromagnetic signals. Fast radio bursts, FRBs, for instance, have been considered as potential candidates for axion-related phenomena, although the connection remains speculative. Another potential observational signal involves axion star collisions. If two axion stars were to collide, or if an axion star collided with a black hole, the resulting interaction could produce unique gravitational wave signatures. These waveforms would differ from those produced by black hole or neutron star mergers, potentially offering a new category of gravitational wave events. Future detectors with greater sensitivity and broader frequency coverage could be capable of detecting such signals, offering a direct window into axion star physics. What makes this even more exciting is the possibility that axion stars could exist in different branches or states. Researchers have theorized the existence of both dilute and dense axion stars. Dilute axion stars are relatively stable and large, with a lower density and mass. Dense axion stars, by contrast, are more compact and could be unstable, possibly collapsing into black holes or decaying into bursts of radiation. The transition between these states is governed by nonlinear dynamics in the Axion field, a rich area of study that combines field theory, quantum mechanics, and general relativity. In some theoretical models, Axion stars can approach a critical mass where their self-interaction becomes strongly nonlinear. At this point, they may undergo a catastrophic collapse, resulting in either a burst of relativistic axions or the formation of a black hole. This critical mass depends on the axion's mass and coupling constant, which are still unknown. These kinds of collapse events could explain high-energy astrophysical phenomena that currently lack a clear source. Even beyond astrophysics, Axion stars intersect with broader questions in fundamental physics. The axion was originally proposed as a solution to the strong CP problem in QCD, which asks why the strong nuclear force appears to respect CP symmetry, a combination of charge conjugation and parity, despite having no reason to. The Peccei-Quinn mechanism, which introduces a new global symmetry that is spontaneously broken, leads naturally to the axion as a pseudo-Goldstone boson. This same mechanism not only solves a thorny problem in particle physics but also provides a plausible candidate for dark matter, and potentially for the composition of these exotic stellar objects. As a result, the search for Axion stars also drives progress in experimental particle physics. Experiments like ADMEX, Axion Dark Matter Experiment, aim to detect axions directly using ultrasensitive resonant cavities and magnetic fields. Although these efforts are not directly focused on Axion stars, any detection of axions would greatly enhance the plausibility of Axion stars as real, physical entities. Similarly, astrophysical observations that constrain the axion's mass and coupling could refine our models of how Axion stars form, evolve, and interact with the cosmos. The potential existence of Axion stars also touches on one of the most profound ideas in theoretical physics: that the universe is fundamentally governed by quantum fields. In this view, what we perceive as particles are merely localized excitations of these fields. Axion stars, then, are not made of particles in the traditional sense but are coherent lumps of the axion field itself, almost like standing waves in a cosmic medium. This makes them not just objects of interest but fundamental manifestations of the universe's deep structure. Even more speculative are the ideas that Axion stars could serve as natural laboratories for quantum gravity. Because they operate in a regime where both quantum effects and gravitational effects are significant, they could offer rare insights into the unification of general relativity and quantum mechanics. Observing their behavior, structure, or collapse could potentially reveal clues about quantum gravitational effects that are otherwise hidden in extreme environments like black hole event horizons or the Big Bang singularity. And then there's the fascinating idea that Axion stars could help solve the puzzle of dark energy, the mysterious force driving the accelerated expansion of the universe. While axions themselves are not dark energy candidates, their interaction with other fields or vacuum energy could lead to emergent phenomena that mimic dark energy on large scales. Some researchers have even proposed hybrid models in which axion-like particles play a dual role in shaping both the small-scale structure of galaxies and the large-scale geometry of the cosmos. Even our understanding of time and entropy might be challenged by the presence of axion stars. If they formed early in the universe and remained stable for billions of years, they could serve as cosmic time capsules, preserving information about conditions in the infant universe. Their internal structure, shaped by coherent quantum fields, might retain imprints of the inflationary epoch or the QCD transition, providing unique data that no other astrophysical object can offer. Axion stars represent one of the most tantalizing frontiers in contemporary science. They are not just theoretical oddities or speculative ideas but are deeply embedded in the architecture of our best physical theories. Their discovery would revolutionize our understanding of matter, energy, and the cosmos itself. From the smallest quantum interactions to the largest galactic structures, Axion stars promise to shed light on the darkest corners of the universe. And for that reason alone, the search for them is one of the most profound scientific quests of our time. The fascination with Axion stars doesn't stop at theoretical boundaries. It stretches into the realm of computational astrophysics, where massive simulations attempt to model the birth, evolution, and interaction of these enigmatic objects. One of the reasons Axion stars have captured so much attention is because they offer an extraordinary testing ground for nonlinear field theory in curved spacetime. Imagine trying to model not just a gravitationally bound system, but a quantum field configuration that maintains coherence over astronomical distances. The challenge is immense, and yet the potential insights gained from these efforts are profound. Advanced simulations rely heavily on solving the coupled Klein-Gordon and Einstein equations, representing the Axion field's behavior and its gravitational interactions. These equations form the mathematical backbone of relativistic boson star models. What makes Axion stars even more interesting is the presence of self-interaction terms in their field equations. Unlike free scalar bosons, Axions have a potential that includes cosine-like terms due to their derivation from the Peccei-Quinn mechanism. These self-interactions lead to stability thresholds, attractor solutions, and possibly even the formation of solitonic cores. In numerical models, Axion stars show a rich variety of behaviors depending on their initial mass, energy density, and surrounding environment. Some configurations evolve into stable, long-lived structures, others oscillate and lose mass slowly through radiation, while still others collapse dramatically under their own gravity. These outcomes are highly sensitive to initial conditions, making the field of Axion star modeling one of chaotic richness. In some models, Axion stars develop quasi-stable, breather states, oscillating field configurations that radiate very slowly over cosmological timescales. These could account for long-lived dark matter clumps. But even in simulations, these field configurations are sensitive to quantum pressure and tunneling phenomena. This means Axion stars are more than just dense blobs of energy. They are living, breathing field structures that pulse with quantum life. And when these simulations are taken to the limit, pushing the mass of the Axion star near its critical threshold, we see extreme relativistic effects emerge. The star's core may begin to approach Planckian densities, leading to questions about the true nature of spacetime in such regimes. There's even speculation that some Axion stars might be dark black holes, objects so dense that they mimic the gravitational effects of black holes without having event horizons. In this scenario, we might mistake Axion stars for black holes based on their gravitational pull, but unlike true black holes, they wouldn't trap light permanently. They might have observable features or emissions, especially during dynamic events like collisions or collapses. This has profound implications for interpreting gravitational wave data, particularly if we detect an event that doesn't match known templates of black hole or neutron star mergers. Moreover, some theories posit that Axion stars might not be made of just one type of Axion field but rather a blend of multiple Axion-like particles, ALPs, with different masses and coupling strengths. This opens up the possibility for multi-field Axion stars, with layered structures much like the layered interiors of planets. The outer shell could be composed of a light Axion field, while the denser core could consist of a heavier Axion species. These multi-field configurations are not just theoretically elegant, they also align well with predictions from string theory, which often produces a landscape of light scalar fields. And this brings us to one of the most speculative, yet exhilarating, branches of Axion star theory, their potential connection to string theory and the so-called Axiverse. In many string theory models, the compactification of extra dimensions gives rise to a huge number of Axion-like particles with varying masses and couplings. This ensemble of particles, the Axiverse, could play a role in everything from dark matter to inflation to vacuum stability. Axion stars, in this framework, could be composed of one or more of these fields and could even help us probe extra-dimensional physics through their macroscopic behavior. Some researchers propose that in the early universe, as these Axion fields began to condense and collapse, they might have interacted with cosmic defects like domain walls or cosmic strings. These interactions could catalyze the formation of Axion stars or imprint signatures in their structure. For example, a collapsing cosmic string loop threaded with an Axion field might leave behind a highly compact Axion star at its center. If such processes occurred frequently, they could have seeded entire halos of Axion stars around galaxies, acting as gravitational scaffolds for baryonic matter to later condense around. As we peer into these theoretical models, another tantalizing possibility emerges, that Axion stars could function as quantum recorders of the early universe. Due to their coherence and isolation from electromagnetic radiation, Axion stars may have preserved subtle quantum information from the early cosmos, acting almost like cosmological memory banks. Detecting and deciphering these imprints could one day offer unprecedented access to physics at energy scales far beyond the reach of any terrestrial experiment. Meanwhile, back in the observational world, new techniques are being developed to identify these elusive objects. Some of the most promising strategies focus on indirect detection through their interaction with other astrophysical bodies. For instance, if an Axion star passes through the disk of a galaxy or grazes a dense molecular cloud, it could create a localized perturbation in the surrounding medium. These disruptions might be visible as strange lensing effects, anomalous stellar motions, or even faint radio emissions. Another proposed detection strategy involves the study of white dwarf cooling. White dwarfs cool over time by radiating away thermal energy. However, the presence of axions, or Axion star interactions, might accelerate this cooling process by providing an additional energy loss channel. By comparing white dwarf temperature distributions to theoretical cooling curves, researchers might constrain the properties of axions and, by extension, the possibility of Axion stars. Interestingly, some anomalies in galactic rotation curves and stellar velocity dispersions might also be attributed to clumpy Axion dark matter distributions, including Axion stars. These would manifest as small-scale deviations from expected gravitational potentials, potentially resolvable with extremely high-resolution spectroscopy and astrometric measurements. Missions like Gaia, which is mapping the positions and velocities of over 1 billion stars, could help reveal subtle signatures of Axion star populations lurking in the galactic halo. On an even more speculative front, researchers have suggested that Axion stars might explain rare high-energy astrophysical events like orphan gamma-ray bursts, short-lived explosions that occur without the supernovae typically associated with them. If an Axion star were to collapse under its own gravity or interact with a compact object like a neutron star or black hole, the result could be a burst of energy without a long-lasting afterglow. While these ideas remain unconfirmed, they represent a growing interest in connecting the behavior of exotic field configurations with observable cosmic fireworks. Ultimately, the study of Axion stars is an interdisciplinary endeavor. It draws from high-energy particle physics, cosmology, general relativity, quantum field theory, astrophysical observation, and computational modeling. Few areas of science demand such a wide-ranging synthesis of ideas, and few offer such potentially revolutionary insights in return. If Axion stars exist, they are not just celestial curiosities, they are keys to the universe's deepest secrets. In every Axion star lies a story, of quantum coherence across the cosmos, of gravity shaping invisible matter, of fields dancing in curved space-time. Their existence would mean that the universe is far richer, stranger, and more beautiful than we ever dared imagine. They invite us to rethink the very nature of matter, the structure of space, and the power of unseen forces. And so, the search continues, not just for evidence, but for understanding, driven by the ancient human impulse to look up at the sky and ask, what else is out there? As we delve deeper into the mysterious world of Axion stars, one cannot ignore the pivotal role they might play in the life cycle of galaxies. In traditional astrophysics, the baryonic matter, the stars, gas, and dust we can see, only accounts for a small fraction of a galaxy's total mass. The rest, cloaked in invisibility, is attributed to dark matter. What if a significant portion of this unseen mass is composed not of exotic WIMPs or sterile neutrinos, but of coherent structures like Axion stars? Unlike diffuse dark matter halos, Axion stars offer a compact, discrete mode of mass concentration. This means their gravitational influence would manifest differently. Instead of a smooth, continuous dark matter background, you could have punctuated, localized regions of high gravitational pull where Axion stars reside. Over cosmic timescales, this granular structure could affect the dynamics of galaxy formation, merger rates, and the development of spiral arms. Simulations that model galactic evolution with granular Axion star distributions instead of smooth dark matter halos have shown promising, albeit preliminary, results. These models suggest that Axion stars could lead to unique density waves in galactic disks, waves that might be observable as irregularities in star formation patterns. These disturbances would act much like ripples, propagating through the structure of galaxies, perhaps explaining some of the asymmetries and anomalies we observe in real galaxies today. One fascinating concept being explored is the possibility that Axion stars could form dark, satellite galaxies, entire clumps of gravitationally bound material that are mostly or entirely invisible. These satellite structures would have too little baryonic matter to ignite star formation, but their gravitational effects could still be detected. In recent years, astronomers have begun to catalog ultra-diffuse galaxies, which are faint and difficult to detect, yet contain large amounts of mass. Some of these could potentially be anchored by massive Axion stars, acting as gravitational cores without any luminous content. On a more localized scale, within our own Milky Way, Axion stars may be lurking in the galactic halo, or even passing through the solar neighborhood. If an Axion star were to travel through or near the solar system, it might subtly perturb the orbits of objects in the Kuiper belt or influence the trajectory of interstellar objects like Oumuamua. Though these perturbations would be incredibly faint, next-generation surveys and spacecraft missions might one day possess the precision needed to detect such subtle gravitational effects. Now let's consider an even more exotic scenario, one that stretches the limits of known physics and enters the domain of speculative cosmology. Could Axion stars have served as primordial seeds for black holes in the early universe? Primordial black holes, PBHs, have long been a theoretical candidate for dark matter and for explaining the presence of supermassive black holes at high redshifts. Traditional black hole formation mechanisms, like the death of massive stars, simply don't act quickly enough to account for the enormous black holes seen in the early universe, mere hundreds of millions of years after the Big Bang. Axion stars, due to their density and potential for collapse, could offer an alternative pathway. If Axion stars formed very early in cosmic history from fluctuations in the Axion field, and if their mass exceeded the critical threshold for gravitational collapse, they could have become black holes without any baryonic progenitor. These PBHs would carry a dark origin, born not of exploding stars, but of collapsing fields. If this occurred frequently enough, it might explain both the missing mass attributed to dark matter and the rapid emergence of massive black holes in young galaxies. Even more intriguingly, if these primordial black holes retained any remnant axionic field structure, they might deviate subtly from standard black hole behavior. For instance, they could emit Axion radiation via superradiance, a process in which bosonic fields extract energy from a rotating black hole. This would lead to observable effects, such as gaps in the black hole mass spin distribution, or even continuous wave signals in the electromagnetic spectrum or gravitational wave domain. Speaking of gravitational waves, Axion stars open new frontiers in multi-messenger astronomy. Mergers involving Axion stars, whether with each other, with neutron stars, or with black holes, could produce unique gravitational wave signatures. Unlike black hole mergers, which have a well-known chirp waveform, Axion star mergers might produce softer, prolonged signals or exhibit frequency-dependent delays caused by field dynamics. These events could potentially fall within the sensitivity range of detectors like LIGO, Virgo, CAGRA, and the future Einstein telescope or cosmic explorer. Moreover, the interaction of an Axion star with a neutron star could lead to a cascade of exotic phenomena. The intense magnetic fields of a neutron star could trigger axion-photon conversion in the star's vicinity, possibly leading to bursts of X-rays or radio waves. Such events could appear as fast radio bursts, FRBs, short, intense flashes of radio waves from distant galaxies, the origin of which remains one of modern astronomy's great mysteries. Some researchers have even proposed that repeating FRBs might be explained by orbiting Axion stars that periodically plunge into a magnetized environment. It's important to emphasize just how central Axions themselves are to the larger question of fundamental physics. Originally proposed to solve the strong CP problem in quantum chromodynamics, a problem concerning the apparent symmetry of the strong nuclear force, axions are not just hypothetical particles. They are a necessary consequence of attempts to unify the standard model with observed reality. The more we study axions, the more we understand that their influence may not be confined to the subatomic world. If they clump together into coherent astrophysical structures, they might connect the smallest and largest scales of existence. The search for Axion stars, then, becomes a search not just for a new kind of star, but for a new way of understanding the fabric of the universe. It's a quest to identify the invisible, to decode the quiet whispers of the cosmos that travel through quantum fields and gravitational echoes. And yet, we remain at the frontier. No Axion star has been definitively detected. No telescope has yet captured the faint glow or gravitational pulse of one of these ghostly beacons. But the theoretical framework is in place. The tools are being sharpened. The universe is waiting. And when we finally find them, these ghost stars, these cosmic phantoms, it will not just mark a triumph of observation. It will be a moment of profound philosophical transformation. We will have glimpsed the structure of reality as it truly is, beneath the veil of visibility, beneath the veil of baryonic matter. We will see the cosmos not as a canvas of stars and galaxies alone, but as a living field of fields, in which even the most silent particles can gather together to sing. The implications of discovering Axion stars stretch far beyond the realm of astrophysics. They challenge our very understanding of matter, energy, and the structure of space-time itself. Imagine a universe where the majority of its scaffolding is invisible not because it is distant, or dim, or hidden behind dust, but because it is composed of matter that behaves in ways we are only beginning to imagine. Axion stars represent such a form of matter, elusive not due to rarity, but due to their fundamental properties, non-interacting, weakly coupled, and yet potentially massive and influential on a galactic, or even cosmological scale. Let's dive deeper into the theoretical underpinnings of Axion stars. At the heart of their existence lies the concept of boson condensation. In contrast to fermions, which obey the Pauli exclusion principle and cannot occupy the same quantum state, bosons, particles with integer spin like axions, can occupy the same quantum state and mass. This property enables the formation of Bose-Einstein condensates, BECs, a quantum state of matter where particles coalesce into a single macroscopic quantum entity. Axion stars are theorized to be astrophysical scale BECs, bound together not by heat or pressure, but by gravity and self-interaction. The existence of a BC at stellar scales is extraordinary. It means that the constituent axions in an Axion star are not behaving like individual particles, but rather as one vast, coherent wave function. This collective state leads to unusual and elegant dynamics, where the classical picture of a star, as a sea of individual nuclei and electrons, gives way to a quantum field dancing in unison. The equations governing this behavior are found in the Gross-Petoevsky equation, a nonlinear Schrödinger equation coupled with gravity. Solving it gives insight into the equilibrium configurations and stability criteria of Axion stars. Interestingly, these stars may exhibit different structural regimes based on their mass. In the low-mass regime, Axion stars are dilute and stable, resembling classical BECs with long-range coherence. As mass increases, so does the gravitational attraction among axions. Eventually, a transition point is reached where the self-gravity overcomes quantum pressure and self-interaction repulsion, leading to a collapse or instability. This defines the boundary between stable and unstable configurations. In certain scenarios, a collapsing Axion star may not immediately form a black hole. Instead, it could undergo a Bose-nova, a phenomenon observed in laboratory BECs where the condensate implodes due to attractive interactions, ejects part of its mass, and then re-expands. This implosion-explosion cycle could, in principle, happen on a cosmic scale, emitting bursts of Axion radiation or gravitational waves. If observed, such events would be both a confirmation of Axion stars and a revolutionary new type of astrophysical transit. The detection of Axion stars thus rests on a delicate interplay of astrophysical conditions and experimental ingenuity. One promising method involves observing gravitational microlensing. When a compact object like an Axion star passes between a distant star and the Earth, it can bend and focus the star's light, causing a temporary brightening. Unlike black holes or neutron stars, which produce predictable and symmetric lensing curves, Axion stars might exhibit subtly different profiles due to their extended but fuzzy mass distribution. Projects like OGLE and the upcoming Roman Space Telescope are equipped to search for such anomalies. Another method involves searching for the electromagnetic signatures of Axion photon conversion. In the presence of strong magnetic fields, such as those near neutron stars or magnetars, axions can convert into photons via the Primakov effect. If an Axion star were to interact with such a field, it could produce detectable radio waves or X-rays. Some scientists speculate that repeating fast radio bursts, FRBs, may be a signature of this process, especially if they occur near highly magnetized regions. There is also a cosmological angle. If Axion stars formed in the early universe, they could leave imprints on the cosmic microwave background, CMB. Their gravitational potential could cause weak lensing of the CMB photons, slightly distorting the otherwise uniform background radiation. Analyzing these subtle distortions, akin to reading tiny wrinkles in a vast fabric, could offer clues about the distribution and mass of Axion stars. Furthermore, the abundance and mass distribution of Axion stars could influence large-scale structure formation. Dark matter is crucial in the cosmic web, the vast network of filaments and voids that make up the universe's structure. If dark matter includes a granular component of Axion stars, it could change the way matter clumps on different scales. This would affect everything from the rate of galaxy formation to the thermal history of the intergalactic medium. Let's not forget the potential role of Axion stars in stellar evolution. In dense stellar environments like globular clusters or galactic nuclei, Axion stars could accrete onto regular stars or compact objects, injecting mass and energy in unusual ways. For instance, if an Axion star collided with a white dwarf, it could trigger thermonuclear runaway reactions, potentially leading to Type Ia supernovae. Alternatively, the collision of an Axion star with a black hole could modulate the black hole's spin and radiation properties, offering another observational handle. Even our Sun might not be immune. Some models propose that Axion stars could occasionally pass through stars like the Sun, inducing temporary anomalies in solar output or helioseismic activity. While speculative, this avenue remains testable with continuous solar monitoring and a growing understanding of solar interior dynamics. In the realm of particle physics, efforts to detect axions directly continue through laboratory experiments such as ADMEX, HAYSTACK, and CASPER. These experiments attempt to detect axions by converting them into microwave or radio signals using high magnetic fields. While they don't directly probe Axion stars, confirming the Axion particle would greatly bolster the case for Axion astrophysics. If axions are confirmed with properties conducive to star formation, such as mass and self-interaction coupling, the door swings wide open to a new era of quantum stellar astrophysics. There's also a profound philosophical implication to Axion stars. Their existence would be a triumph of theoretical prediction, demonstrating the power of quantum field theory and general relativity to describe not just the microcosm or the cosmos, but the bridge between them. It would suggest that the universe is governed not by disparate rules and separate domains, but by a unified language, mathematical, elegant, and deeply quantum. And so we find ourselves at a crossroads. The search for Axion stars is not just a scientific endeavor, it is a quest to understand the unseen structure of reality. Like the ancients who looked to the night sky and saw patterns in the stars, we now look beyond the visible, seeking patterns in the invisible fabric that holds galaxies together. When Axion stars are finally discovered, if they are, their light will not dazzle like the supernovae, nor pulse like the neutron stars. They will whisper, not shout. They will bend light, but not emit it. They will alter orbits, but not collide. Yet in their silence lies power. In their invisibility, truth. And in their mystery, a promise that the universe is far stranger, more beautiful, and more intricate than we ever dared to believe. Yet the story of Axion stars does not end with their potential detection. In fact, much of their scientific intrigue stems from the vast landscape of what they could become and cause in the long-term evolution of the universe. They are not just astrophysical relics or exotic objects trapped in dark matter halos. They may actively shape the fate of galaxies, influence fundamental particle physics, and even offer windows into alternative cosmologies that challenge the Standard Model itself. To truly appreciate the scale of their potential influence, we must look into the thermodynamic and dynamical stability of Axion stars across cosmic time. These stars, especially in the dilute regime, could persist for billions, if not trillions, of years without significant dissipation. Their longevity alone makes them potential cornerstones of long-term cosmic evolution. Unlike baryonic stars that exhaust their fuel and die as white dwarfs, neutron stars, or black holes, Axion stars may avoid this fate altogether, simply existing in a near-permanent quantum state until they are disturbed by external events or instabilities internal to their structure. These instabilities, though rare, could carry profound consequences. Imagine a galaxy filled with dilute Axion stars drifting slowly through the dark matter halo. Over time, gravitational encounters may cause two Axion stars to merge. The merger could push the resulting mass over a critical threshold, triggering collapse into a dense configuration, or even a black hole. This natural buildup of mass and phase transitions within Axion stars could serve as a kind of dark, stellar evolution, a parallel to the evolution of visible stars, but governed not by fusion, but by quantum gravitational balance. This evolutionary pathway invites further speculation. Could Axion stars be the missing link in understanding the mysterious population of intermediate mass black holes? These black holes, ranging from 100 to 100,000 solar masses, remain elusive and are poorly explained by existing models of stellar collapse or galactic nuclei dynamics. However, a cluster of Axion stars slowly merging and collapsing could yield precisely this outcome, without the need for standard baryonic matter. If true, it would mean that a portion of the cosmic black hole population arose not from massive stars, but from the gravitational death throes of quantum condensates. Let us also consider the possibility that Axion stars, due to their gravitational compactness and exotic field configurations, could interact with spacetime in non-trivial ways. Some theorists have explored how scalar field objects like Axion stars could act as gravitational lenses not just in the classical sense, but through wave lensing. In this scenario, the interference of gravitational waves as they pass near or through Axion stars could reveal distinctive diffraction patterns, akin to how light bends through a prism, but on a cosmic scale. Future gravitational wave observatories such as LISA or the Einstein telescope might detect such phenomena, providing indirect but powerful confirmation of these structures. Moreover, Axion stars may not be uniform in their composition. Depending on the model, the Axion field could support multiple bound states or mixed field configurations, potentially giving rise to what some call oscillons, or Q-stars, objects that oscillate periodically or carry multiple conserved charges. These hybrid stars could exhibit semi-stable behavior, glowing faintly in the radio or gamma-ray spectrum through suppressed decay processes. Theoretical models suggest that certain energy levels could resonate with vacuum fluctuations, creating faint emissions that would be detectable only with ultrasensitive instruments, possibly revealing the internal quantum structure of spacetime itself. One of the most compelling prospects for Axion star research lies at the intersection of cosmology and information theory. There is growing interest in whether objects like Axion stars encode information in fundamentally different ways than conventional matter. If axions are topological excitations or linked to string theoretical modes, then Axion stars could act as repositories or resonators for deep cosmological information, perhaps preserving conditions of the early universe in their wave functions. If proven, it would imply that some of the answers to the Big Bang, inflation, and even the nature of time itself might be encoded in these silent beacons. The complexity of this possibility expands further when we consider alternate axion-like particles, ALPs, which arise in many string theory frameworks. These particles, which differ slightly from the QCD axion in mass or coupling strength, could form their own stars or merge with existing axion stars, altering their properties in unpredictable ways. The interaction of different axionic fields could create interference patterns, nodes, or chaotic oscillations, potentially giving rise to time-varying dark matter signatures detectable in laboratory experiments or astronomical surveys. This naturally leads us into discussions of the Axiverse, a theoretical framework suggesting that our universe contains a vast array of axion-like fields, each with different properties and roles. Within the Axiverse, Axion stars could come in a spectrum of sizes, densities, and masses, much like ordinary stars do. Some may be microscopic, with masses barely greater than a mountain. Others may be titanic, approaching the mass of a supermassive black hole but without the event horizon. This diversity introduces a level of richness to cosmic structure that is currently invisible to telescopes but could be revealed by new generations of instruments sensitive to axion-photon coupling, gravitational wave anomalies, or microlensing distortions. From the technological standpoint, studying Axion stars has also motivated the creation of a new breed of experiments and detectors. High-finesse microwave cavities, superconducting resonators, haloscopes, helioscopes, and dielectric stacks are all being refined to push the limits of sensitivity to Axion signals. These devices, while built to detect single-particle events, may also become crucial in identifying large coherent sources like Axion stars, especially if these stars decay or interact with magnetic fields. One fascinating proposal even suggests embedding nanosatellites across the solar system to form a distributed Axion detection network, where even small anomalies could be tracked and triangulated back to a dark source. On the more speculative end, some physicists have begun exploring whether Axion stars might serve as natural laboratories for testing the limits of quantum gravity. Because they exist at the nexus of quantum field theory and general relativity, Axion stars may support localized violations of classical energy conditions, potentially producing regions where exotic space-time geometries emerge, such as warp-like bubbles or traversable wormholes. While no current model supports stable traversable wormholes linked to Axion stars, the possibility remains tantalizing, especially if future theoretical work identifies self-sustaining energy configurations arising from scalar fields. In this light, Axion stars are no longer just a curiosity, they become central figures in the drama of cosmic evolution, technology, and theoretical physics. They are the dark reflections of ordinary stars, driven not by fusion, but by the deep symmetries of the universe. They may be far older than any star we see, and far more numerous. And they may hold secrets not just about matter and energy, but about the origin, structure, and ultimate destiny of the cosmos itself. And as we look forward, we must remain open to the possibility that the first confirmed Axion star may not come from a dramatic burst or cosmic flare, but from a whisper, a quiet, regular anomaly in a magnetar's radio emission, a slightly asymmetric gravitational lensing event, or an unexplainable flicker in the polarization of light passing through space. In those moments, the veil may lift just enough to reveal a fragment of the dark and quantum scaffolding that holds our universe together. The concept of Axion stars, when traced to its theoretical roots, is not merely a footnote in cosmology, it's a potential paradigm shift. The quantum fields that underlie their structure beckon us to reconsider our assumptions about the composition of the universe, the nature of mass, and even the architecture of spacetime. Their very existence, still speculative but rigorously modeled, compels us to explore areas where particle physics and general relativity intersect in unexpected, subtle, and perhaps revelatory ways. To fully grasp this, we must take a deeper dive into the intricate quantum mechanics that undergirds Axion stars. Unlike conventional particles, axions are governed by the rules of quantum field theory on cosmological scales. Their behavior is described not merely by positions and momenta, but by field configurations, wave functions that can extend across kilometers or even light years. The axion field oscillates at frequencies determined by its mass, typically in the range of microelectronvolts, and this oscillation gives rise to time-varying energy densities that affect gravitational interactions. This leads to the concept of a coherent field, where a vast number of axions share a single quantum state, acting like a giant quantum object rather than a loose collection of individual particles. This coherence is crucial, It allows for the formation of solitonic configurations where the quantum pressure balances the gravitational pull. Such solitons are at the heart of Axion star stability. These configurations, which can persist over billions of years without dispersing, are a natural result of the nonlinear Schrödinger-Poisson equations that govern self-gravitating scalar fields. But what happens when this balance is perturbed? Theoretical work has shown that Axion stars exist on a spectrum from stable, dilute configurations to metastable dense ones. As we've touched upon before, dilute Axion stars are well behaved. Quantum pressure and gravity reach a harmonious equilibrium. Dense Axion stars, however, are perched on the edge of catastrophe. They are vulnerable to what physicists call Bose-Ova collapse, where quantum effects fail to counteract gravitational compression, resulting in a rapid implosion that could generate bursts of radiation, gravitational waves, or even convert the star into a black hole. Understanding these collapses isn't merely an exercise in applied mathematics. It's a glimpse into cosmic alchemy, where quantum coherence gives way to gravitational singularity. Now imagine, if you will, an entire population of Axion stars forming early in the universe. Some collapse, seeding black holes. Others persist, acting as gravitational seeds for galaxy formation. Still others slowly accrete dark matter and evolve. This scenario paints a cosmos where dark matter is not uniform and cold, but structured, dynamic, and deeply quantum. Such a picture is radically different from the standard cold dark matter model, which treats dark matter as a pressureless fluid. If Axion stars are real, then dark matter is not just inert scaffolding, it's alive with structure and evolution. This hypothesis is not just supported by speculation. Simulations of dark matter halos incorporating scalar fields suggest that the centers of galaxies may host solitonic cores, regions where the density profile flattens, rather than peaks. Observations of dwarf galaxies and their rotation curves, which often defy the predictions of standard dark matter models, align better with these core-like profiles. Could these cores be the gravitational signatures of Axion stars? If so, we're already seeing their fingerprints, just not recognizing them for what they are. The implications grow even more profound when we consider the potential interactions between Axion stars and standard matter. Though axions interact incredibly weakly, they are not entirely aloof. In the presence of magnetic fields, axions can convert into photons and vice versa, a process known as the Primakov effect. If an Axion star were to pass through a strong magnetic region, say, near a neutron star or pulsar, it could produce bursts of radio waves or X-rays. These transient events might already be hidden in our astrophysical data, masquerading as unexplained fast radio bursts, FRBs, magnetar flares, or other high-energy phenomena. To that end, many scientists have begun combing through existing catalogs of radio transients, looking for repeating or one-off events that match the theoretical profiles of Axion star interactions. This search is painstaking but full of promise. The universe is noisy, yes, but within that noise, patterns emerge. And those patterns might lead us straight to our first encounter with an Axion star. But let us not stop at the observational frontier. The theoretical possibilities of Axion stars invite thought experiments that verge on the philosophical. Consider the question: could a sufficiently advanced civilization harness the properties of Axion stars? If one could manipulate Axion fields, perhaps by engineering magnetic fields or controlling gravitational environments, it might be possible to extract energy from Axion star decay, use their field configurations to encode information, or even manipulate local spacetime in novel ways. These are speculative ideas, to be sure, but they highlight just how rich the physics of Axion stars could become in a broader cosmic context. And speaking of broader context, one cannot ignore the potential connection between Axion stars and the arrow of time. Some physicists have posited that Axion fields, due to their phase-dependent behavior and cosmological evolution, could play a role in the emergence of temporal asymmetry. In simpler terms, the gradual relaxation of Axion fields across the universe might help explain why time appears to flow in one direction, why entropy increases, why we remember the past and not the future. If Axion stars act as localized nodes in this temporal field, they could encode information not just spatially, but temporally, forming a kind of cosmic memory grid. The metaphysical implications are staggering. Could Axion stars carry the imprints of cosmic history within their fields? Could we, by decoding their internal structure, access relic information from the earliest epochs of the universe? Could they act as archival structures, quantum fossils of the inflationary past? This line of inquiry is speculative, yes, but not ungrounded. Already, physicists are probing the informational content of quantum fields, and Axion stars may well represent the first naturally occurring high-capacity storage structures in the universe. Furthermore, the potential for Axion stars to impact the structure of black holes deserves renewed scrutiny. Traditional black hole models obey the Noether theorem, which states that all information about infalling matter is lost, save for mass, charge, and spin. But if Axion stars collapse into black holes, do their field configurations somehow survive? Do they leave behind unique imprints on the event horizon? Could Axion-induced quantum effects resolve the black hole information paradox? These are open questions, but they're gaining traction in the intersection of high-energy theory and quantum gravity. We must also consider the role of Axion stars in cosmic inflation. Some models suggest that Axion-like fields could have driven the rapid expansion of the early universe. If so, then Axion stars might not just be leftovers. They might be echoes of inflation, frozen waves from the moment time began. Studying their distribution, coherence, and interactions could help us reverse engineer the initial conditions of the universe, a goal long sought, but never achieved. Let us reflect on the grandeur and subtlety of Axion stars. They are not bright like our sun. They do not burn with nuclear fire. They do not scream across the cosmos like quasars or supernovae. They are silent, slow, invisible, yet potent beyond measure. They are whispers of the quantum world, echoes of symmetry breaking, guardians of dark energy and dark matter alike. They remind us that the universe is not always what it seems, that behind the stars we see may lie others we can only imagine. And as we continue to build better telescopes, launch more sensitive detectors, and refine our mathematical models, we edge closer to the day when Axion stars transition from theory to observation, from shadow to light. On that day, the universe will grow not only more complex, but more complete. The path to fully understanding Axion stars is far from straightforward. As we journey further into the theoretical domain, one of the most fascinating areas emerging involves the potential topological structures that Axion fields may exhibit. These aren't just ephemeral features. They are mathematical fingerprints of deep field behaviors, and Axion stars may host complex topological configurations such as knots, vortices, or domain walls. A domain wall is a type of topological defect that can arise when a discrete symmetry is spontaneously broken. If the early universe underwent such a symmetry-breaking transition and axions emerged as a byproduct, it is possible that stable or metastable domain walls were formed. These walls, essentially regions where the Axion field changes from one value to another, could become trapped or folded into localized regions, possibly forming the seeds around which Axion stars grew. This adds a topological narrative to the Axion star story, where their formation is not just governed by gravity and quantum mechanics, but also by the hidden geometries of field evolution. Now imagine, in the early universe, a turbulent sea of Axion fields, filled with defects, oscillations, and fluctuations. Within this chaos, localized pockets of high field coherence form, proto-Axion stars. Over time, these regions attract more Axion particles, growing denser, more structured. Some collapse under their own gravity. Others reach equilibrium. The variety in their fates adds richness to cosmic structure. Some may become black holes, some dark matter halos, others long-lived quantum stars roaming interstellar space. But there's more. If we take the nonlinear Schrödinger-Poisson equations and add self-interactions for the Axion field, such as a cosine potential, which reflects the field's periodic nature, we get entirely new behaviors. Self-interacting Axion stars can undergo oscillations, emit scalar radiation, and in some simulations, even bounce, after attempted collapses, forming quasi-stable oscillating configurations. These are not simply static balls of dark matter, they are dynamic, pulsing objects, with internal rhythms dictated by the field's energy landscape. This internal dynamics opens the door to an extraordinary possibility: resonant interactions. In certain configurations, Axion stars could emit scalar radiation at discrete frequencies. These emissions, while weak, could add up over time and across populations, possibly producing detectable signals, an Axion analog to gravitational wave backgrounds. While we have yet to confirm such emissions, models predict that under certain parameters, Axion stars might literally sing in the scalar field, broadcasting their existence into the void. So what would it take to hear them? Projects like the Axion Dark Matter Experiment, ADMX, Haystack, and Casper are already trying to detect axions via their coupling to photons and nucleons. These experiments typically use resonant cavities, cryogenic conditions, and tunable magnetic fields to catch the tiniest signals. But future iterations could adapt to search for modulated signals, those that might come not from free axions, but from axions bound in coherent, structured states like Axion stars. This may require not just new instruments, but new theories. How do Axion stars interact with standard model particles? What are the cross-sections for conversion, annihilation, or decay? Could certain stellar environments amplify these interactions? For instance, the intense gravitational and magnetic fields near pulsars, magnetars, or black hole accretion disks could act as cosmic amplifiers, making axion-photon conversion more likely. Observing such hotspots might reveal repeating or transient features tied to Axion star behavior. The beauty of this research lies in its multidisciplinarity. Particle physics, quantum field theory, general relativity, and astrophysics converge here. And beyond the physics itself, there is also the computational challenge. Simulating Axion stars at high resolution demands massive computing power and clever numerical schemes. The field is evolving rapidly thanks to advances in GPU-accelerated computing, enabling researchers to study the collapse, merger, and oscillation of Axion stars with increasing fidelity. And what about binary Axion stars? Could they orbit each other like neutron star pairs, eventually merging? Theoretically, yes. If such a merger occurred, it could result in a burst of scalar radiation, gravitational waves, or even a black hole. The gravitational wave signature would likely be distinct from that of neutron stars or black holes, less intense, but possibly longer-lived, depending on the dynamics. This gives rise to another frontier, Axion gravitational wave astronomy. Current detectors like LIGO and Virgo are not tuned to such events, but future detectors like LISA or DESIGO might be. By analyzing subhertz gravitational wave spectra, scientists could search for signs of compact object mergers that don't fit existing templates. If an Axion star merger was ever recorded, it would be a revolutionary moment, providing direct evidence for axions, compact bosonic objects, and a new form of stellar physics. Still, there's more to the Axion saga. The landscape of string theory, our leading candidate for unifying quantum mechanics and gravity, predicts not just one axion, but potentially thousands of axion-like particles, ALPs, each with different masses and couplings. This Axiverse scenario suggests that Axion stars might come in many varieties, from ultralight stars spanning galactic cores to more massive, compact stars invisible to all but gravitational detectors. If true, this means the cosmos is teeming with hidden structure. An entire taxonomy of Axion stars may exist, some stable, some unstable, some isolated, others embedded in dark matter halos, some cold and ancient, others young and volatile. Understanding their diversity may require a new classification system, akin to the Hertzsprung-Russell diagram for regular stars. And these stars, in turn, may have their own life cycles. A small Axion clump might grow by absorbing ambient dark matter. It could interact with other clumps, merge, fragment, or collapse. Under tidal stress from galactic rotation, it might stretch or even emit radiation. These dynamic processes suggest a field of Axion stellar evolution, one that mirrors and complements our understanding of baryonic stellar life cycles. So where does this leave us? We are standing at the threshold of a new astrophysical paradigm. Axion stars, once speculative mathematical curiosities, are emerging as serious candidates for a variety of cosmic phenomena. From solving the dark matter mystery to revealing the nature of quantum fields in curved spacetime, they hold keys to some of the deepest questions in science. And the journey is only beginning. Every new telescope launched, every new detector calibrated, every new simulation run may bring us closer to the moment when Axion stars transition from the shadows of theory into the light of observation. On that day, we will not just have discovered a new class of star, we will have uncovered a new chapter in the cosmic story, one written not in fire and fusion, but in symmetry, fields, and the whispered harmonies of the quantum universe. If we allow ourselves to dwell further on the implications of Axion stars in the vast symphony of cosmic evolution, we begin to realize they are not just relics or byproducts of the early universe, but potentially active players in its unfolding narrative. These enigmatic structures may influence the motion of galaxies, the distribution of matter on cosmic scales, and even the evolution of other celestial bodies that interact with them. Their gravitational pull, subtle yet persistent, could shape stellar orbits within galaxies in ways we've yet to fully grasp. Axion stars, unlike traditional baryonic stars composed of atoms and plasma, do not emit visible light. This makes them inherently elusive. However, their gravitational influence is real. Consider the delicate dance of stars at the edge of spiral galaxies. Observed velocities suggest the presence of unseen mass. While the mainstream interpretation favors diffuse dark matter halos, an alternative or complementary picture could be one in which these halos contain a population of Axion stars, moving silently through the dark, warping spacetime in ways just sufficient to hold galaxies together. In this scenario, Axion stars act as the granular building blocks of dark matter halos. Rather than a smooth, fog-like distribution, dark matter may be clumpy, with each clump being a coherent, self-contained Axion structure. Simulations have shown that such clumpy dark matter can still match large-scale structure formation observations, and in some cases, they offer better fits to certain anomalies, such as the central density profiles of dwarf galaxies, known as the cusp core problem. Dwarf galaxies in particular are fertile grounds for Axion star research. These small galaxies have relatively shallow gravitational wells, making them sensitive to the behavior of whatever dark matter they contain. If Axion stars populate these regions, their quantum properties, such as a minimum scale of localization due to the uncertainty principle, may prevent the central density spike predicted by cold dark matter models. This could offer a natural explanation for the flat density cores seen in many observations. Even the phenomenon of gravitational lensing may be impacted. Axion stars, depending on their mass and size, could act as femtolenses, or picolenses, producing minute distortions in the light from distant quasars or gamma-ray bursts. Detecting such effects requires extraordinary precision, but as our instruments improve, it may become possible to identify characteristic lensing patterns consistent with compact bosonic objects. This leads us into the domain of observational signatures. What would be the smoking gun for an Axion star? First, there's the potential for Axion photon conversion in magnetic fields. When axions traverse regions of strong magnetic fields, like those near pulsars, magnetars, or galaxy clusters, they may convert into photons. If an Axion star passed through such a region, it could emit a transient radio or X-ray signal, a flare that might mimic other astrophysical processes but differ subtly in its frequency profile or polarization. Second, if Axion stars form binaries or interact with dense environments, they may trigger explosive events. Some theories propose that collisions between Axion stars and neutron stars could lead to fast radio bursts, FRBs, those mysterious millisecond-long flashes of radio energy observed from deep space. The collision could induce a rapid conversion of axions into photons, releasing a burst of electromagnetic radiation. Though speculative, this idea is gaining traction as more is learned about the environments surrounding FRBs. Moreover, there's the curious possibility of thermal emissions, not from the Axion stars themselves, which do not emit thermal radiation in the classical sense, but from interactions they might trigger. For example, if an Axion star were to drift into a dense molecular cloud, its gravitational influence could induce heating, compression, or ionization effects, indirectly producing observable signals. Though weak, these emissions might appear anomalous, hot spots with no apparent cause, and could be targets for deep sky surveys. On the theoretical front, researchers are also exploring whether Axion stars could be solutions to the Einstein-Klein-Gordon system with rotating metrics. In other words, could there be spinning Axion stars, boson stars with angular momentum? The answer appears to be yes, although such objects would have more complex stability conditions. Their formation would likely require highly asymmetric initial conditions or mergers, but their presence could add an entirely new dimension to the taxonomy of Axion stars. Spinning Axion stars might emit scalar radiation at different harmonics, possibly even producing unique polarization signatures. Their angular momentum could also allow for interesting accretion phenomena, perhaps leading to observable modulations in surrounding matter or fields. Just as neutron stars with strong magnetic fields can emit pulsar beams, rotating Axion stars might produce scalar field pulses, a signal not yet detectable, but theoretically conceivable. Another branch of exploration involves the potential interaction between Axion stars and cosmic strings, hypothetical one-dimensional topological defects that may have formed during early universe phase transitions. Cosmic strings, if they exist, might snare Axion stars, influencing their motion or even triggering particle conversion events. The interaction could be dramatic, leading to bursts of radiation, gravitational waves, or even fragmentation of the Axion star. Such events, if detected, would offer not one but two pieces of evidence for beyond standard model physics. Speaking of gravitational waves, it's worth reiterating their central role in this quest. Though Axion stars are less dense than black holes or neutron stars, their mergers or collapses could still generate gravitational wave signals, albeit weaker and at different frequencies. These signatures, especially if enhanced by self-interactions or phase transitions within the star, could be distinguishable from known compact object events. Over time, as we accumulate more gravitational wave data, statistical methods might reveal outlier events consistent with exotic compact objects. In a more distant speculative realm, we might even consider the role of Axion stars in cosmic inflation. If axions were present in abundance in the early universe, and if some formed coherent structures shortly after the Big Bang, could they have contributed to inhomogeneities in the cosmic microwave background, CMB? Could their dynamics have left faint fingerprints in the polarization or temperature anisotropies of the CMB? While mainstream models do not require such components, future high-precision CMB missions, such as CMB-S4, may reveal small-scale anomalies that require new explanations. If Axion stars are implicated, it would suggest that these objects have been part of the universe's story from the very beginning, influencing its shape and structure in ways only now becoming apparent. And beyond cosmology, there's an even wilder possibility. Could Axion stars play a role in life itself? This may sound absurd at first glance, but consider the following. If Axion stars are relatively common, and if they interact weakly but meaningfully with electromagnetic fields, then it's conceivable that their presence could affect planetary environments. Subtle modulations of local electromagnetic fields, changes in radiation flux, or gravitational interactions might influence things like atmospheric chemistry or magnetic shielding. While purely speculative, it opens an entirely new interdisciplinary frontier, one where astrobiology, quantum field theory, and astrophysics converge. Indeed, as we move deeper into the 21st century, our exploration of Axion stars may reflect the next great scientific synthesis, a merging of physics, astronomy, cosmology, and computation to answer not just what the universe is made of, but how its most elusive components shape the visible world. The road ahead will be long, complex, and full of uncertainty, but also rich with the promise of discovery. And at the center of it all may be the Axion star, an invisible beacon in the cosmic dark, guiding us toward a new understanding of matter, energy, and the deep architecture of space and time. The journey into the world of Axion stars is not just a mere pursuit of an obscure particle or hypothetical celestial object. It is an exploration into the very nature of the universe itself. It challenges our assumptions about the properties of dark matter, the behavior of fundamental particles, and the larger structure of space-time. This journey represents a paradigm shift, a move beyond traditional astrophysical frameworks, into realms where quantum mechanics and cosmology intersect in fascinating, potentially world-altering ways. As researchers push the boundaries of our observational capabilities, the search for Axion stars continues to be a central focus of many astrophysical projects. The discovery of Axion stars would open up an entirely new avenue of understanding about the universe. It would be a groundbreaking moment, comparable to the detection of gravitational waves or the first image of a black hole's event horizon. These milestones mark the triumph of human ingenuity and the relentless pursuit of answers to fundamental questions about the universe. But what does this mean for the future of scientific inquiry? It's more than just an academic question, it touches on the very fabric of our reality. The potential discovery of Axion stars, their properties, and their interactions with ordinary matter could redefine much of what we know about the cosmos. Imagine a universe where the invisible, the unknown, and the most intangible forces of nature reveal themselves not through the lens of visible matter but through the delicate interactions of mysterious particles, like axions. This is a universe that behaves very differently from the one we thought we knew. Moreover, such discoveries could pave the way for new technologies and applications. If axions and their associated fields could be manipulated, could they be harnessed for new forms of energy? Could these particles have roles in future quantum computing systems, offering faster processing capabilities by tapping into the strange properties of axion-based systems? This might sound like science fiction, but such breakthroughs have occurred in the past in the realms of technology and materials science. Concepts once thought impossible have become the foundation of the technologies that drive our modern world. The discovery of Axion stars could, in time, lead to such a revolution, reshaping the future in unimaginable ways. As we continue to investigate Axion stars, scientists are also refining the methods and tools required to detect these elusive objects. The concept of Axion detection itself is incredibly challenging, requiring a level of precision and sensitivity that current technology can only dream of achieving. However, we are inching closer to this dream every day, with collaborations and advancements in fields like quantum optics, particle physics, and gravitational wave astronomy. In the realm of particle detectors, the use of high-powered laser systems, extremely sensitive detectors, and superconducting magnets could potentially uncover the subtle interactions between axions and photons. The axion-photon coupling, one of the critical aspects of axion detection, may one day be measured through specialized experiments that harness the power of lasers in strong magnetic fields. In these environments, axions could transform into photons, and those photons could be detected, providing the first real evidence of axion stars or axion-like particles in our universe. Similarly, advancements in space-based telescopes and observatories will also be crucial for identifying axion stars. These stars, though invisible to traditional optical telescopes, may become visible through their gravitational effects on surrounding objects, the detection of gravitational waves from axion star mergers, or even through the faint electromagnetic radiation produced when axions interact with powerful cosmic phenomena. Future missions that focus on precision measurements of cosmic backgrounds, dark matter distribution, and gravitational lensing will be vital in identifying the signatures of axion stars. Additionally, as our understanding of the quantum properties of axions grows, we may come to realize that their role is not just confined to cosmology or particle physics. The question arises, could axions, in some way, explain the mysteries of consciousness or the nature of perception itself? This sounds speculative, but when we consider the nature of quantum field theories and their interactions with the human brain, the potential overlap between axions and the brain's electromagnetic field becomes a possibility worth considering. After all, axions are believed to interact with electromagnetic fields in unique and complex ways. If they can influence the large-scale structure of the universe, could they also influence the microscopic structure of biological systems? Could axions provide the key to understanding the connection between the mind and the universe? This line of thought takes us into the philosophical and metaphysical implications of axion star research. If axions are indeed fundamental building blocks of reality, their discovery could challenge our understanding of existence itself. It could lead to new questions about the nature of reality, the relationship between the observer and the observed, and the limits of human perception. How much of the universe exists in a form that we can't yet perceive? How much of it is hidden, not because we lack the technology to see it, but because we lack the understanding of how to detect it? These are profound questions that might be raised in the wake of Axion star discovery, pushing us to rethink the very structure of knowledge. Furthermore, one of the most intriguing aspects of Axion stars is their potential to solve some of the most persistent problems in cosmology. The nature of dark matter and its effect on galaxy formation is one such challenge. The discovery of Axion stars would not only provide a potential candidate for dark matter but also offer new insights into the nature of galaxy formation, structure, and evolution. It would be a critical piece of the puzzle, explaining why galaxies behave the way they do, why they rotate at the speeds they do, and why their structures appear so uniform across the universe. Axion stars could, in effect, provide the missing piece of the cosmic jigsaw puzzle. But even more than that, the discovery of Axion stars might serve as the key to unlocking the mysteries of the universe on the largest scales. The existence of axions could lead to new ways of understanding the origins of the universe itself, potentially offering clues to the nature of the Big Bang, the evolution of spacetime, and the very laws of physics. Axion stars may have formed in the early universe, and studying their properties could reveal how the universe transitioned from the primordial soup of the Big Bang to the richly structured cosmos we see today. In a more speculative realm, Axion stars could even provide answers to some of the most profound questions about the future of the universe. For example, what will happen to the cosmos in the distant future? As the universe continues to expand, dark matter, whether in the form of Axion stars or something else, will play a crucial role in the long-term evolution of galaxies and clusters. If Axion stars are indeed a fundamental component of dark matter, they may be instrumental in shaping the fate of the universe. Could Axion stars act as guardians of the cosmos, maintaining the balance between expansion and contraction, preventing a cosmic collapse, or facilitating one in some distant era? Theories about the ultimate fate of the universe, whether it ends in a big crunch, a big rip, or some other form of cosmic cataclysm, are deeply tied to the properties of dark matter and energy. Understanding Axion stars may therefore be essential for predicting the universe's final chapter. Their behavior could provide vital clues about how dark matter interacts with other forces, how spacetime itself behaves under extreme conditions, and whether we are on the brink of a grand cosmic transition. Ultimately, the exploration of Axion stars represents a merging of science, imagination, and discovery. It offers a glimpse into the unknown, a horizon filled with possibilities that stretch far beyond our current understanding. As we continue to probe deeper into the nature of dark matter, Axion stars will remain a central, albeit elusive, mystery, waiting to be uncovered by the next generation of scientists, engineers, and explorers. And perhaps, when we finally detect them, we will realize that the universe is even more wondrous and strange than we ever imagined. The excitement surrounding the discovery of Axion stars is more than just a fleeting interest in one particular type of astrophysical object. It is a broader reflection of the growing desire to understand the unseen forces that shape the universe. With each step we take in unraveling the mysteries of axions, we come closer to deciphering the hidden aspects of the cosmos. This search is not just about uncovering a specific particle or phenomenon. It's about expanding the frontiers of human knowledge and pushing the boundaries of what is possible in science. In the search for Axion stars, scientists have devised several groundbreaking strategies to probe the universe for signs of these elusive objects. These strategies rely on a deep understanding of the physical principles governing axions and their interactions with other particles and fields. One of the primary methods for detecting Axion stars is through their potential gravitational effects on nearby objects. Since Axion stars are thought to have an incredibly high density of mass, their gravitational influence could lead to observable effects, even if these stars themselves are not directly detectable. By studying the motion of nearby stars or the bending of light around suspected Axion star systems, researchers could gather crucial data to confirm the presence of these objects. One such method involves the detection of gravitational lensing. When light from distant stars or galaxies passes near a massive object, such as a black hole or a potential Axion star, it bends around the object due to its gravitational field. This bending of light, known as gravitational lensing, could reveal the presence of Axion stars even if they do not emit detectable radiation themselves. If an Axion star exists in a region of space, its gravitational pull would distort the path of light from background sources, allowing astronomers to detect this distortion and potentially identify the presence of the Axion star. Gravitational wave astronomy is another promising avenue for detecting Axion stars. The merger of two Axion stars, or the collision of an Axion star with another type of stellar remnant, could produce ripples in the fabric of spacetime that propagate outward as gravitational waves. These waves, which were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, are incredibly subtle but offer a unique method for studying events that occur in the most extreme environments of the universe. If Axion stars exist, the detection of gravitational waves from their mergers or interactions with other objects could provide the first definitive evidence of their existence. Additionally, Axion stars may produce faint but detectable electromagnetic radiation under certain conditions. When axions interact with other particles, such as photons or electrons, they may produce faint signals in specific parts of the electromagnetic spectrum, including X-rays or gamma rays. The search for such radiation could be conducted using space-based telescopes and observatories that are designed to detect high-energy photons. For example, instruments like the Chandra X-ray Observatory and the upcoming James Webb Space Telescope may play critical roles in this search by providing detailed observations of regions where Axion stars might be located. Another intriguing possibility is the use of direct detection experiments aimed at observing the interactions between axions and ordinary matter. Axions are theorized to be extremely weakly interacting with matter, which makes them incredibly difficult to detect. However, under the right conditions, it may be possible to observe the interaction of axions with electromagnetic fields. Experiments such as the Axion Dark Matter Experiment, ADMEX, are attempting to detect axions by looking for the conversion of axions into photons when they pass through strong magnetic fields. These experiments are still in their infancy, but they offer a promising path toward discovering axions and potentially detecting Axion stars in the future. The detection of Axion stars would not only be a scientific breakthrough but would also have profound implications for our understanding of fundamental physics. One of the primary reasons for the interest in Axion stars is their potential connection to dark matter, the mysterious substance that makes up a significant portion of the mass in the universe. Dark matter is thought to exist because of its gravitational effects on visible matter, yet it remains undetected by conventional means. Axions are a leading candidate for dark matter, and if Axion stars are found to exist, it would provide compelling evidence for the Axion dark matter hypothesis. In addition to its potential role in explaining dark matter, the discovery of Axion stars could also provide insights into other areas of physics, such as the unification of forces, the nature of quantum mechanics, and the behavior of matter in extreme environments. If axions are indeed a fundamental particle, understanding their properties could lead to new theories of particle physics that go beyond the standard model. This could have profound implications for our understanding of the universe's origins, the nature of space and time, and the fundamental laws that govern the behavior of matter and energy. Furthermore, the discovery of Axion stars could offer a new perspective on the evolution of the universe. Axion stars, if they formed during the early stages of the universe, could provide valuable information about the conditions that existed shortly after the Big Bang. By studying the properties of these stars, scientists could gain a deeper understanding of the cosmic inflationary period, the formation of galaxies and large-scale structures, and the interplay between dark matter and ordinary matter in shaping the universe's evolution. The study of Axion stars could thus provide a new lens through which we can explore the history of the cosmos and its eventual fate. As we continue to probe the mysteries of Axion stars, it is important to remember that science is always evolving. What we know today is only the beginning, and there may be countless discoveries waiting to be made as our understanding of axions and their role in the universe deepens. The search for Axion stars is not just a quest for one specific type of celestial object. It is a journey that could fundamentally alter our perception of reality itself. This journey will require collaboration across multiple disciplines, with physicists, astronomers, and engineers working together to develop new technologies and methods for detecting axions and understanding their properties. The challenges are immense, but the potential rewards are equally great. In many ways, the search for Axion stars is symbolic of the broader human pursuit of knowledge, a relentless drive to explore the unknown, to push the limits of our understanding, and to answer questions that have intrigued us for centuries. The future of Axion star research is incredibly exciting, and the possibilities are endless. As our technology advances, so too will our ability to observe and understand the universe at deeper and more intricate levels. The discovery of Axion stars may one day become a cornerstone of modern astrophysics, offering profound insights into the nature of the universe, the fundamental forces that govern it, and our place within it. And as we continue to look to the stars, we may find that the answers to some of our most profound questions lie in the most unexpected places, in the very fabric of the cosmos, hidden within the mysterious and elusive Axion stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.